Okay, so good morning, everyone. Let me start by thanking the organizers for putting together a fantastic program. It's a pleasure and honor to be here to present the work joint with Lee Fleming from Berkeley and Lena Vretenik, a PhD student at our group in KU Leuven. So, as all of you know, science is important for driving technological innovation inside companies, yet many firms, particularly large firms, have been scaling back internal investments in scientific research and instead seem to increasingly rely on externally conducted academic science. So I think there is lots of work actually demonstrating that this reliance on academic science strongly correlates with firm innovation and performance. Yes, I think relatively speaking, there's less work actually at looking at some of these micro-level mechanisms of how companies could actually leverage scientific insight from academia to develop corporate technology. And so this broader research question we hope to kind of contribute to with our work. So academic science is typically viewed as a public good, so meaning that it's accessible to all companies, it's beneficial to all without kind of restrictions or competition. Of course, in practice, this might turn out to be quite difficult, I think for two main reasons. So first, there is a search problem. So there is a huge and kind of ever-expanding body of scientific knowledge, which makes it difficult for companies and also engineers within those companies to actually search and find potentially relevant scientific discoveries, which might have commercial potential within the company. So apart from the search problem, of course, there's also an absorption problem. So we know that scientific knowledge tend to be specialized and also partly tacit in nature, meaning that part of this knowledge kind of remains embedded within the academic scientists who make a particular scientific discovery. So these people run the experiments in the lab, they experience failures, they have some ideas about potential applications, and not all of that knowledge is kind of codified and transferred to the publications alone. And so companies willing to benefit from this science need kind of both access to the knowledge, but also the absorptive capacity to understand and use that knowledge. So in this paper, we look at two specific mechanisms that might allow companies to do so. So first, we look at interpersonal connections between corporate inventors inside companies and academic scientists. So those connections might actually help corporate inventors to become aware early on about new scientific discoveries who might have potential and perhaps get access to some of the relevant knowledge. But just getting access to this knowledge might not be enough. And so secondly, we also look at the absorptive capacity of those corporate inventors. So do they actually have the right scientific expertise to kind of understand and use that knowledge for the development of corporate technology? So our prediction is that having kind of close ties to the academics might be important, but only insofar the corporate inventors inside the company do have the capacity to actually understand and use that knowledge. So to study this question, we use three layers of data. So first, we collect academic paper twins in life sciences, where nearly identical discoveries are found by different academic teams around the same time. I'll come back to that in a minute. So then we identify company patents who actually cite those academic papers, which will be our outcome measure in the analysis. And so this is our proxy for the fact that indeed there was kind of a corporate invention building on scientific prior art from academia. And then third, we construct an interpersonal collaboration network linking all academic scientists in life sciences to all corporate inventors on US patents. And so that allows us to kind of look at the shortest path between any academic scientist and any corporate inventor. And so this will be our main explanatory measure. And I think there's plenty of work looking at direct collaboration between academics and people inside companies. But so here we try to map the entire network structure, also allowing us to look at kind of the role of indirect connections between the two groups. So a bit more about the network. So we collect all data on disambiguated authors in PubMed, so covering all scientific work in life sciences, all disambiguated inventors on US patents, and we also have a crosswalk between the two. So for any individual, we have both their patents and or their papers. So in this data, we have both instances, a patent or a paper, and the individuals being the authors on those patents or papers. And in line with prior work, we're going to assume that a quadraship link is kind of creating a tie between two individuals through which knowledge potentially might flow in the future. So then we construct the network where each node is an individual. A tie, as I just explained, is kind of a collaboration link from the past. And then, of course, each new paper potentially might kind of update that network. So we yearly update the network until 2009. And then the network includes roughly 12 million individuals, most of which are scientists who only publish, some of which are just inventors who only patent, and then roughly 300,000 individuals who have both a paper and a patent at a particular point in time. And so again, this data allows us to kind of compute the interpersonal connection between two individuals, which we simply do in line with prior work as the shortest path in the network between an academic scientist and a corporate inventor, which will be our main explanatory measure. Now, looking at how kind of close ties or personal connections, how that affects the transfer of knowledge, of course, we face an important identification problem, namely those scientists which are close in the network probably are doing different types of science. So science which is more applied, which has higher commercial potential, and so they're more likely to get cited, not because they're close in the network, but because of the type of science that they're doing. And so the problem we face is that you need to separate the network effects from kind of the content and the commercial potential of the science. And to do so, in line with prior research, including work by Michael Picard and also Matt, so we collect academic paper twins where two nearly identical findings are published around the same time by two independent academic teams. And then we identify company patents who only cite a subset of those twin papers. So the papers are very similar, but only one of those is being cited. The way we exploit this, again, in line with prior work, is that we use the uncited twin paper to kind of construct a counterfactual or pseudo-citation, allowing us in the estimation to kind of control for the content and the commercial potential of that science. So to collect academic paper twins, so I won't go into detail, but so we carefully follow the methodology and the data of Michael Picard. So our sample includes 250 roughly paper twins, so simultaneous discovery, accounting for roughly 500 papers. So those papers are published very close to each other in time, and they're really highly similar in content. And interestingly, you see that 90 out of those approximately 250 tend to be published back to back. So in the same journal, same volume, same issue, one right after the other in terms of the pages. So here is one example. So in 1998, two independent teams jointly discovered that a signal called CD40 can activate killer immune cells without needing helper cells. So this was an important scientific discovery. The papers got published back to back in Nature. So these papers, they're almost identical in content. And importantly, this was also a crucial discovery for the development of vaccines or treatments for people with a weakened immune system. And so this commercial potential is demonstrated by the fact that we trace more than 250 US patents which are actually citing those twin papers. And so interestingly, of those citing patents, some of which are just citing the first paper, so the Bennett et al. Paper, another share is only citing the second paper, so the Schoenberg et al. Paper, and the remaining part is citing both at the same time. So here is one example. So 4 years later, in 2002, there is a patent filed by Argenx and Pfizer on a cancer and autoimmune disorder treatment involving human antibodies targeting CD40 to trigger the immune response system. So clearly, this corporate invention is building on the academic twin discovery, which identified the role of CD40, yet the patent is only citing one of the two twin papers. So it's only cited Bennett et al. And not the other paper, which is almost identical in content and published back-to-back in Nature. So here we map the interpersonal connections, so the shortest path in the network between the inventors on the corporate patent, whose nodes are represented in the right corner below by the black light bulb symbols, the academic scientist on the cited paper, whose nodes are represented by the checked drawing board symbols on top, and also the academic scientist on the uncited twin paper, whose nodes are represented by the unchecked drawing board symbols. And what you see here is that indeed there was kind of a shortest path of one between the corporate inventors and the academic team which is being cited. So here, Ronald Gladieux, working in Pfizer, previously collaborated with Richard Flavel, who is an immunologist at Yale. So they published a paper 8 years earlier. So here there is a shortest path of one, while the unsighted team, there is only an indirect connection. So suggesting that indeed, perhaps being close to these people might actually allow the transfer of knowledge. So in terms of our estimation samples, so we have approximately 2,100 of those real citations, so company patents citing a subset of the twin papers. So for each citation that we observe, we then construct a counterfactual citation by linking the same citing patent to the uncited twin paper. And so then the final sample has approximately 4,200 paper patent diets, half of which are the real citations and half of which are the counterfactual. So to estimate the model, so we use a conditional logit model. Our outcome measure is simply a binary indicator equal to 1 in case it's a real citation, 0 in case it's the counterfactual. And so as explained before, so the main explanatory measure is the social distance, the shortest path in the network between the authors on the paper and the inventors on the patent. So this is a count measure ranging from 0 to, I think, 10 in our data. But in the main specification, we use binary indicators for social distance. For instance, social distance 0 is equal to 1 in case the shortest path is 0, meaning that one of the authors on the paper is also one of the inventors on the patent. As another example, so social distance 1 is a binary indicator equal to 1 in case the shortest path is 1, meaning that there is not an overlap between the two teams, but there's kind of a prior collaboration tie directly between the two. As a final example, so social distance 2 equal to 1 in case the shortest path is 2. So meaning that there is no direct collaboration, but there is kind of a common collaborator between the academics on the paper and the corporate inventors on the patent. Now, so this model is estimated with fixed effects at the paper twin patent level, so arguably controlling for the near identical content and the commercial potential of the paper, but also for the type of the technology, the inventors on the patent, or the company who is filing the patent. So here is the main results. Here we show the predicted probability of a company patent citing an academic paper for different levels of social distance between the two teams. So what you see is that the predicted probability of citation kind of gradually decreases the more distant distance in the network between the scientist and the inventor. So what you see is that the different binary indicators for social distance 0, 1, and 2, so they're each significantly different from one another, but also the higher order distances of social distance, so 3, 4, and 5 or more, while the binary indicators for social distance 3, 4, and 5 or more are not significantly different from one another. So we interpret this as demonstrating the threshold of the network in facilitating the transfer of knowledge, where beyond a social distance of 2, so beyond having a common collaborator with the academic team, having any connections is not having any role anymore. So here we estimate the exact same specification, but we use a simple count measure of social distance. And so across different specification, we see that kind of 1 degree of separation closer to the academic scientist increases the probability of citation between 16 and 26% in relative terms, relative to the baseline likelihood of citing. Of course, an important remaining identification concern is that those corporate inventors may kind of intentionally form ties to academics when they anticipate using their knowledge. And of course, this would cause us to kind of overestimate the true causal effect of having ties on potential transfer of knowledge. So in the paper, we don't have an instrument or we don't have an experiment, but we try to identify to what extent such an endogenous formation of ties is kind of driving the results that we observe. So let me just give 2 examples. So first, we exclude all observations in which the shortest path is 0 or 1. So meaning that there is a direct collaboration between the two teams, or there was kind of a direct collaboration in the past. And so arguably, these are cases which most likely kind of reflect intentional tie formation to kind of facilitate the transfer of knowledge between the two teams. So even if you exclude all those, we still find that having connections kind of increases the likelihood of citation. So secondly, we recompute our measure of social distance using only ties established before the publication of the twin papers, here by design kind of excluding any ties that are intentionally or unintentionally formed after the scientific discovery, so to actually exploit it commercially. And again, if we do this, the results still hold. So next, we look at the absorptive capacity of the corporate inventors. So arguably having close ties to the academics might not be enough to actually benefit from that for the development of corporate technology. Arguably, an important condition is that the corporate inventors who have the ties actually have the absorptive capacity to kind of understand and leverage the knowledge that they might get through these connections. And so the way we do this is that we construct two proxies for the absorptive capacity of those corporate inventors. So specifically, we look at whether they're actually themselves engaged in scientific research, proxied by scientific publications in the year or 2 years before the patent filing. And secondly, we look at how close their scientific expertise is to the twin papers by looking at their own scientific work, their paper embeddings, and see how closely that's related to these twin papers. So what we find is that in order to benefit from having kind of close connections, indeed, it's important for those corporate inventors to be actively engaged in scientific research. So without that, having close ties does not matter. And secondly, having closely related scientific expertise seem to strengthen the effect of having ties. So that actually seems to benefit. Okay, so let me conclude. So as you know, academic science is important in driving innovation inside companies. Although academic science is typically viewed as a public good, so we find that having actually very close ties to the academics who make a particular scientific discovery seem to actually have a strong influence on firms' ability to kind of commercially exploit those discoveries. So we find that having close ties, so direct connections to the academics, seem to work best, but also indirect ties up to 2 degrees of separation seem to facilitate the transfer of knowledge. So at the point where you have kind of a common collaborator with a team who makes a particular scientific discovery. I think interestingly we find that the majority of all knowledge transfer, or the majority of all citations, actually happen through those indirect connections. So demonstrating kind of the benefits of the network in kind of providing access to kind of more diverse scientific knowledge, while the knowledge available through direct collaborators is, of course, necessarily more restricted. And then finally, we find that network access and having individual absorptive capacity seem to be complementary. And so we hope this work can contribute to a better understanding of kind of the mechanisms, the micro-level mechanisms of how companies could benefit from academic science. Thank you.
Perfect. Thank you. Very nicely on time. Very happy to have Adam discussing this paper.
Well, thank you very much, and thanks to the organizers for inviting me to talk about this paper. Patents, citations, like close to my heart, so it's a pleasure. Okay, so what do I like about this paper? You know, every 2 years I teach one class in Scott Stern and Pierre Azoulay's PhD course on innovation policy, and I teach a class on measurement. And one of the things I always say is, you know, everybody talks about networks, but very few people actually do much more than just like drawing pretty pictures with it. And so what I really like about this paper is that it takes the notion of the innovation system as a network quite seriously and says, okay, let's try to measure how much these network linkages actually matter. And I think that's a really important frontier for us as a group, as a research group, and so I like that a lot. They've built this really big data set of scientists, essentially authors and inventors, essentially people on patents, and so they have this network, and then they use the citations from patents to papers as a proxy for knowledge flows, and they say, what can we say about that? So I like this agenda a lot. Sam put this picture up, but it all went by very quickly, so I'll do it once more so that we're sure we know what's going on here. So this is the probability that a particular patent cites one of the two papers, and this first bar is one of the inventors is actually an author on the cited paper, and you can see there's like a 70% chance that that's the paper that gets cited. Then this next one is one of the inventors is a co-author with one of the authors on the paper, and that's still pretty high. And then this one is one of the inventors is a co-author with someone who is a co-author with one of the authors on the paper, and then, and so forth. And they take this out through the whole network. And so, overall, basically what this says is that for these direct links and up to one or two steps through the network, that's distinctly higher. I think it's, oh, sorry, I didn't mean to go on. I think it's worth noting that these numbers are still pretty high. And Sam mentioned that if you add up all of the citations, something like half of them in total are coming from this people who have no direct or first order connection. So the stuff is apparently flowing very far through the network. Okay, then they have these what I call second order effects, which is that first order effect is interacted with, are the inventors themselves still active in science, and do they work in an area that's closely related? And they find that those are significant. I think this is interesting in and of itself on absorptive capacity. I'll also comment in a minute that I think it possibly reinforces that the first order effect maybe is actually real, because if the first order effect was some kind of artifact, you wouldn't necessarily expect it to interact with these absorptive capacity measures in the way that it does. Okay, now, this is patent citations as a proxy for knowledge flows. Now, I have to say the way the paper is written, I think the word proxy maybe appears in the paper, but a lot of the discussion kind of has the flavor that these citations are knowledge flows. And that's not really right. We all kind of do that. That's why the mea culpa is up there. But I think some discussion of how the proxy might actually differ from the thing we really want to measure, the knowledge flow, I think is needed. And, the standard view is that, or I shouldn't say the standard view, my view is that citations are, noisy as an indicator of knowledge flows, but in large samples, that noise should get washed out and we should find big trends. This is not a super large sample, and it's a very special context, these twin papers. So I think we need to think about that a little bit. They mentioned this paper by Matt, that most of the citations from patents to papers, as distinct from citations from patents to other patents, do typically come from the inventors. It's not the examiner that's putting them on there. One thing that's important, Sam put up a picture of the front page of a patent as an example, but in fact, the vast majority, again, we know from Matt, most of these citations are actually not from the front page. Most of them are from the description, and that has a different legal status. So I think we need to think about that. As I mentioned, I like that they have these second order results, because I feel like that helps us think that this is something real. Sorry, I screwed up on my slide construction here and forgot to delete something from the second slide. I think we need to think about the fact that these are twin papers. These are literally not just similar papers, but the same scientific finding. I think the front page references, it's particularly tricky to think about, like what does it mean as a legal matter if there are two pieces of identical prior art? Do I cite both of them? Do I cite one or the other? I talked to Lisa Wallet about this, who's like the world's leading expert on prior art. And what she said was that technically they're different publications, So if they're both prior art, they should both be there, but her view was the examiner probably doesn't care. There is this issue of it's actually legally possible that one of them enables the invention in a way that the other doesn't. For example, if they did the experiments differently to come up with the same result, it's conceivable that there is some legal reason why you'd cite one and not the other, but it's hard to know. And then the citations in the text are not governed by any legal rules. So they can be anything. They can be, you know, some aside as to why we did it the way we did it. And, you know, so I just think we need to be aware that that's all going on there. Then just a few miscellaneous thoughts. You know, this paper pairs idea is super clean. You know, in this world of identification is the most important thing. I can see why you wanted to use these twins. But, you know, it's super clean at the expense of being kind of low power and a little hard to interpret. I'd like to see what it looks like if you kind of do Jaffe, Henderson, Trachtenberg and just find very similar papers that are not identical. What does that look like? Okay, it's not quite as clean, but we might learn more about that. Secondly, I would drop the continuous proximity measure. The chart we both put up shows that the relationship is not linear and it's not continuous. And so I think that's potentially just misleading. There's no reason why you can't interact some version, you don't have to do every single one, but some version of your categorical variables instead of the continuous measure. And then this is a cheap point because it's easy for me to say you should do it. I know it's a huge amount of work. Somebody should be looking at linguistic similarity rather than just citations. And then just to finish, I think it's really interesting to think about the fact that if you take the paper literally, you know, knowledge flows through many nodes of the network are actually quite important. I'd like to think that this is true and that we've shown it. I'm a little skeptical. It's one of these things that's like too good to be true. I'm a little worried that it's just capturing a lot of stuff that isn't otherwise captured and maybe isn't really telling us very much. But I think that's worth thinking about. You know, in some sense, this shouldn't have worked. These papers are the same. It's like, why would we expect there to be any differences between who cites them? Shouldn't really mean anything, and yet they seem to. So I just think that that's interesting. And then, you know, going forward, in some sense, I'd like us all to be working on pushing this frontier and testing these network relationships in different ways so that we can really understand more what's really going on here. Okay, thank you.
Thanks a lot, Adam, and you very nicely illustrate how complementary a discussion can be of a paper, so it brings so much more value out of the paper together with this presentation. So thanks a lot for that here. So if you have questions, always use the mic.
Since I brought the mic, I'm going to use it. I want to know what policy intervention you would suggest. You know, is it more conferences? Is it, you know, how do we benefit from this thing that you've uncovered?
Yeah, yes, we collect. Yeah.
I just wanted to double click on and say a little bit more on the kind of legal strategy around these citations. I mean, so Lisa obviously would know better than me, but I mean, there's also, my recollection is, if essentially you don't have to cite cumulative prior, or you only have to cite cumulative prior. So if there's two things that are actually identical, like legally citing one of them is enough in some sense, right? So if it's a pure twin, now the date matters. I think that like the earlier priority date one is also the one you have to cite. But more related to your absorptive capacity type measures and your network measures, there's also this duty of candor, right? You have a legal obligation to cite stuff you know about, and not, you know, that otherwise it's a fraud on the patent office and all sorts of other bad things. So, yeah, I guess consistent with something Adam was saying, I wonder how much of this can be explained through legal strategy and kind of just patent law stuff as opposed to absorptive capacity type considerations. I wonder further if actually looking separately at the front page versus in-text citations is one way to get at that, and maybe even European, I mean, I don't want to create more work, but even if you look at the European side where you don't have a duty of candor, and you know, you could see some similar stuff. So, but exciting work.
Really like the paper. Just a small question about and I don't really know like the kind of patent literature that well, but I was wondering if, to what extent does strategic citing play a role in this? Because if you know, maybe you choose to cite one paper because you are like previously like kind of like allied researchers, and that I guess has implications on the interpretation of the result as a network being having an effect on the flow of knowledge.
This is very interesting, and I appreciate the effort that went into constructing this. I guess there are two things that I'm wondering about. One of them is about whether there's any value in looking at physical proximity in these networks as well. So, I mean, you're looking at social distance, but does physical proximity also map in some way onto this? And it doesn't seem like it would be that hard to geolocate people. The other is about treating the network in some sense as exogenous, and I mean, I think, and I'm not sure that I'm persuaded that that makes sense, regardless of the identification strategy, in the sense that these are corporate decisions. I mean, so the inventors are, maybe employed by the business, by the corporations. They got hired somehow. They got hired for some reason. The businesses decide where to locate, so that comes back to the distance thing. And so, there's some purposive activity that generates co-authorship or generates a social network, and you're just sort of treating that as present, but it's not just something that got laid down like a set of railroad tracks that somebody built 100 years ago. So
this is sort of related to Josh's point, but you sort of had me at hello with that picture, and if that's true, that should have implications for whom you hire. One reason to hire a seasoned academic is for their ties. There are many ties to many people. So a different paper, follow-on paper, could be to see the implications for hiring patterns.
I was looking at the curve, and I think sort of similar to what Adam was saying about sort of how it plateaus at a pretty high level, it sort of sounds like eventually you would find the other paper anyways, and that this is sort of hastening my sort of search to find that information. And so if there was some way to set this up also for how fast does information diffuse, or how quickly does this end up in a patent based on the social distance, I think that would be a different but also really interesting study.
I guess I just wanted to propose that a much more provocative way to frame this is people don't read journals, because if they do, they should know about this other paper, right? And so if they're only learning about their stuff from the networks, then what are journals doing?
Yeah, thanks a lot. So can I also add the question? So if I understand correctly, you only look at the co-authorships as links here, but the links could also run through co-inventors here. So if one of your co-inventors has some kind of ties to science here, there could also be an indirect link. Is that also part of the network that you are tracing?
Yeah.
So that was, sorry. Yeah.
Yeah, so thanks everyone. Great comments, very useful. Thanks also, Adam. So first point, citation as a proxy for knowledge spillovers. Of course, I fully agree. So this is clearly a limitation. So we don't just use front page, so we use all citations, also in text. I think in the paper we also try to separate, also look at specifically in text to see, because that should be a better measure. But I mean, I think the result went in the right direction, but the data set is not huge, so it didn't give us a lot of power. On twin papers, again, fully agree. So I think the external validity is not that high, but in a follow-on paper, we actually do the same exercise, but then for all patent-to-paper citations. Of course, then we don't have a counterfactual, but then we look at papers which are cited at least twice by a patent, and then that's actually a relatively large share, also representing a very significant share of all citations. And then instead of looking at who's being cited, we look at who is being first or quicker than the others. And there we find the same result. Like the closer you are, the quicker you are in kind of picking up that scientific discovery. So So that also relates to the other comment. In terms of the textual similarity between the paper and the patent, I think we looked at that and control for that. So they're really very, very similar in content, the text of the two twin papers. So that actually doesn't make a big difference. In terms of how far the knowledge can travel, so actually beyond 2 degrees, we don't find any significant effect anymore. So if you're 3 or 10 degrees of separation away, there's no difference anymore. So I think that also makes sense that you need to be relatively close to actually have an
You
effect.
also said that overall, more than half of the citations come from patents that are more than 2.
Yeah, that's right. But I also referred to like shortest pad of 2 has more citations than the shortest pad of 0 or 1. Yeah.
If many of the citations are coming from patents
Mm.
where there is no 0 first or second order link, I think there is a deep question of how do we interpret that? Do we interpret that as saying stuff really flows far through the network, or do we interpret that along the lines of Bitsy's question of, well, maybe the network doesn't really matter?
Sure. I think not all of the knowledge you rely on comes through the network. So I think it's just sometimes, and it's, so increase the likelihood, but just not all the time. Yeah. On the question of Bhavan, so indeed, great question. Do you need to cite to 2? And perhaps the first ones, we do control for which paper gets published first in the estimations. Do they know both papers or not? So Matt actually did an inventor surveys in his paper with Michael, and they asked about, okay, why do you cite this one and not the other? And then they mentioned like, well, this is the one we know. We rely a bit on that. So in terms of policy interventions, I think there are many things we know already, like science parks, of stimulating collaboration, being located at the same site, having PhDs together with industry. All these things I think could make a difference. In terms of strategic citing friends, let's say, the paper which are closest. So I think we also find the results if you do exclude any close ties, like 0 or 1 degree of separation away. So I think it would be unlikely that you're going to give like an indirect referral to someone to kind of please them. In terms of the overlap with geographic proximity, again, we compute the shortest distance between the academics and the inventors in terms of the miles, so how close they are related to each other, and control for that. In terms of network, whether that's exogenous, fully agree. So we cannot, of course, exclude that it's kind of endogenously formed. The way we try to deal with that is, yeah, as I show, we try to see, okay, to what extent is that driving the results. Question on hiring implications, yeah, fully agree, thank you, great comment. And then priority in kind of pick up the idea. Again, that's what we do with the follow-on paper, seeing kind of who's quickest in citing the same scientific prior art. Anyway, thanks everyone, very, very useful.
Yeah, thank you very much. Okay, so the next paper that we have is on a topic which is actually a very sensitive topic. We discussed this yesterday. It's about gender-inclusive innovation. So fortunately, we're not in Hungary. You would have been cut. So it will be present. It's a paper joint Matt Marks and Joël Waldvogel, but you're going to present because Matt Marks got up this morning, very early last night. So
Thanks very much.
yeah. Okay.
So, thank you to the organizers for including this, and this is joint, as you say, with Matt and with Frank Mueller-Langer. As you know, Matt is a great producer of public goods for the profession, and he has a public service announcement before we're done at the end of the discussion. So don't let me not allow that to happen. Okay, so this paper is about the effects of inclusive innovation, and innovation we all know is really important for growth, and we would like to make use of sort of all of society's innovative potential. Women have sort of lagged. I mean, in creative and in innovative activities, they've been less represented, but there have been some influxes. In an earlier paper, I looked at books. Women have become more than half of book authors. Now, some people have said to me, well, that's not really innovation. So I thought, time to return with Matt and Frank and think about innovation in the context of patenting and academic authorship. There, the influxes are substantial, nothing like books, but from 5 to 9%, roughly a doubling, from 5 to 20% in academic authorship. So there are some influxes one could look at. And what we're interested in doing in this paper is trying to quantify the benefits of these influxes. How large are they? And who wins? That is, like, who benefits? Which citers, users of these innovations are benefiting from them? And we take two different approaches here. We take a descriptive empirical approach, but we also build an explicit equilibrium model so we can, well, quantify the benefit, because it involves a counterfactual. So anyways, tiny bit of background here. You know, as you know, for various reasons, women have lagged men in participation in innovative activities. There's a big literature on this, and you're all cited. There's also an interesting literature on sort of the influx of gender on the direction of inventive activity. Very interesting, and you're all cited. Actually, if you're not, please email us. No, seriously. But we're not really about that. A little bit about that. We're more just about, let's make use of the other half of, you know, the human distribution and see what we get. So just a little bit of background here. For example, if you look at a number of people scoring 700 or above on the GRE, basically women have doubled the pool as women have gone into, you know, getting educated and so forth and getting ready for grad school. Moreover, if you look at PhD, you can't really see this. What you're meant to see is from 1950 to 2020, these all rise. The share of grad school or PhD recipients who are female have risen to different extents in different fields, but it's rising. All of this is just to suggest that there's a reason to expect a female influx to deliver valuable innovation. Okay, not that I would have doubted it, but this is trying to be empirical and not sort of, you know, knowing the answer in advance. All right, so what I want to do now is give just a sketch of the theory. Later on, there'll be some explicit stuff with even a few equations. Sorry about that. But for now, let's just get a sense of what we're about. So to value the female influx, what are we thinking about? We'd like to compare the present. So the present is, you know, a context in which the influx has happened to a counterfactual environment in which the influx did not happen or had not happened. So what do we need to do this? Well, number one, we need a choice of which of the female innovations to remove from the status quo. Number two, though, if you believe in equilibrium, you also need a way to think about, well, what might we have gotten instead then if the women hadn't entered? So we need a model of the response, and that's kind of the hard part in some sense. We also need a way to turn the extant set of innovations into some value measure. So we need to be clever or stupid. That's that wonderful line in Spinal Tap, fine line between stupid and clever. But we need to be clever and do something. Okay, so we're going to use an industrial organization approach to this problem. What is demand? Well, demand, current innovators, now we'll just use that word to mean authors of articles and inventors of patents. Current innovators choose which of the extant innovations to, you know, buy or to cite. So citation, knowledge flows, buying, it's a floor wax, it's a dessert topping, it's everything. What do you want? Anyways, but you know, in the spirit of I.O., again, innovations may be substitutable for one another. We have to allow for that. So, you know, it's possible you get a bunch more, but if they're perfect substitutes, it's not that valuable. Now, you know, moreover, the available choice set is going to determine what we call innovators' surplus, which is just a direct analogy to consumer surplus, you know, in demand theory. On the supply side, we have potential innovators deciding whether to enter. And so entry here means creating an innovation, writing an article and publishing it, you know, creating a patent. And they do so if the expected citations exceed fixed costs. So imagine there's some revenue associated, and they do so if it exceeds fixed costs. And again, removing the female influx is going to increase the return to male innovation. All right, so we're going to have an equilibrium model in a few slides, but first, there are a bunch of empirical questions that are suggested by this that I think descriptive empirical questions that speak to whether we would expect value here or you know, a valuable, highly valuable female influx. Like, did the influx happen? I kind of already said it did. How valuable are female innovations? And I'm sorry, I'm using these shorthands, but yeah, forgive me for just using these shorthands. How valuable are the female innovations? How substitutable are innovations for one another? And does additional innovation expand the market? Again, you know, by analogy to sort of I.O. and products, you know, if you have a new product and it doesn't draw anyone from non-consumption, it's probably not very valuable. Okay, so for data, we have, on the article side, we use the Microsoft Academic Graph data set, so basically 50 years, 65 million articles in all their fields. We see the citations to them. We can also divide the citations to them into citations coming from all articles, articles by women, articles by men. Now, there's a whole bunch of work, and I got a hats off to Matt here, but so we have to figure out the genders of the authors, and a lot of names are ambiguous, so we have this LLM-based way of checking and getting, you know, peripheral information for doing a kind of a neat job of this. We're going to refer to an innovation as female if half or more of its innovators are female. We have the analogous thing on the patent side. The patent office has you know, created and made available similar data, almost the same time period, 70 to 2020. Again, we have all the citations they receive, but then we have the citations from men, from women. Okay, so the female influx happened. Yep, doubling or so in patents, quadrupling or so in articles. You know, it's to different extents in different fields. Like on the article side, we get to over 30% in fields like psychology and sociology, still pretty low, like 5%-ish in engineering. On the patent side, you know, we don't have a sociology patent category, but we, you know, on the high side, we have like 15% in biotech and pharma, and we have like 5%, you know, engines, pumps, and turbines. Whoops, that's not good. Ooh, okay, we're back. All right. Now, it's kind of interesting to note that although there's been this big increase in the number of innovations from women, there hasn't been a decline in the number of innovations from men. So sort of like, to a first approximation, there's no obvious evidence of displacement. We're going to allow for displacement, the possibility in the equilibrium model, but it's not like one's going up, the other's going down, nor is it that way within field. All right, but this is maybe one of the more important descriptive facts. So are female innovations valuable? So let's just define the following. QVF is citations received by vintage V female innovations, and NVF is the number of such innovations. So this is the citations per innovation for the female innovations by vintage in which the innovation occurred. Here's the same thing for men. Well, let's think about the ratio of the two, this RV as the relative value of the female innovations across vintages over time. And we'll do the same thing from female citers and from male citers. But let's just start with the overall. All right, so here's some pictures. The dark or the solid line is just the overall. And it's roughly constant over time, maybe a little bit above one, a little bit below. But what's interesting about that is in the background, female innovation is doubling on the patent side and quadrupling on the article side. So it's not like we're drawing, you know, farther down in the distribution. That's not what's going on, right? So that's sort of evidence to make you think that this is going to be valuable. Another thing you can take away from this picture is that that upper line is female. It's the same calculation, but for citations from female citers, and this is sort of tendency for women to cite innovations by women, and a little bit lower the other line for men. Okay, now do additional innovations expand the market, right? So here what we're going to do is think about the available innovations in year T, now calendar year T, which is the sum of all the things that have come up since then, and regress the number of citations received by area A, you know, category A in year T on the number of available innovations. And we have, you know, year fixed effects and area fixed effects. And what's kind of interesting here is that all the coefficients are positive, okay? So what's consistent with expansion of the market, that is the fields in which there come to be more things to cite, there are more citations received, okay? So, and that would be consistent with innovations not being close substitutes for one another, the expansion of the market idea. All right, so far, female influx looks valuable, like but the descriptive analysis kind of only takes you so far. It doesn't give you a way to say how valuable, because, you know, we haven't really addressed the equilibrium question at all. All right, so the structural model here, and apologies. But so on the demand side, we're going to just define QJ, citations to innovation J, suppress the year subscript. Think of M as the market size. So what is market size in these models? It's the number of instances in which someone's making a decision to cite. So of all the innovations appearing this year, think of the reference list in the back, like the number of potential references is in some sense the market size, and then there are a bunch of discrete choices of which things to cite. So SJ is, think of it, it's almost like a market share, the tendency to cite innovation J. Now I want to get to some way to characterize the value of the choice set, so just a little more notation to get there. S is the sum of those S's, so that's the inside share, and 1 minus S is S0, the outside share. So you may remember this logit mean utility idea, delta J, which is something we'll lean on a lot, ln Sj minus ln S0. But we're going to just take it like one step further and do nested logit, so we have this important parameter sigma, which indicates or reflects the extent to which innovations are substitutes for one another. So delta is going to be an important animal for us. The choice set, the set of things available to be cited, is described by this set of delta J's. You could think of as the qualities of these innovations. And the quality is really just measured by the extent to which they're getting cited. All right, so we want to summarize the value of the choice set with this D of n function. It's kind of a trick in a sense. D of n is the summation from 1 up to n of e to these qualities divided by the substitution parameter. And you can think about this aggregate value of quality thing as being divisible into the female part and the male part. And we're going to trade on that. But again, it's determined by the distribution of the value of these deltas. Now we can express the outcomes of interest, the things we care about in this study, like innovator surplus, for example, in terms of these D functions. So this is just a ripoff of the consumer surplus formula, but notice that it's monotonic in dm plus df. The values of these, basically the pile of innovations available to be used. Okay, so again, back to the two-part thought experiment. We're going to remove female innovations. How are we going to do that? Well, we're going to basically drive the D0. 0 is for the status quo, 1 is for the counterfactual. Drive it down essentially to the relative proportions of female to male in 1970. So we're going to take away from every vintage after 70 some female value to drive it back to where it was. Right, so the red thing is the new. And this reduces the innovator surplus to, now we've made it red, to something that's going to be smaller. And you could call this the naive estimate of the welfare effect. The status quo in the numerator, this counterfactual that we've just taken women out in the denominator. No male entry response. But the harder part is actually, because removing women is going to raise the returns. Removing the female influx is going to raise the male return. So let's think about this. The solid line in this picture shows expected citations to the marginal entering male innovation. Where that dark solid line crosses N0, the status quo number of male innovations, well, that defines the fixed cost of entry, K0M. Now, when we remove women, we're going to raise the return to male innovation, to the dashed line. And so we're going to go, well, where does that cross? How come this isn't working? Oh, okay, try this. There we go. So where does that cross the fixed costs? Well, at N1, which we've rendered in blue. Okay? So, the task here is to find N1. The thing that's hard about this is that we're thinking about in some sense, what's the value of products that didn't get introduced? So we have to have kind of a sensible idea, or maybe sensible, clever, stupid, whatever. We have to have an idea about how good would the next products be. Okay? So that's where we get back to this dm of nm function. So one more kind of hard slide in some sense. How does this dn evolve with nm? Well, entry order matters a lot, and its interaction with quality predictability. So suppose you knew in advance how good everything was going to be, which, by the way, is not the world. Then things would enter in order of best to worst, and you'd have like that really curved line as D of n. On the other hand, if you couldn't predict at all, it'd be random, so in expectation, it would just be that solid line. Well, now, Goldilocks truth comes from, if you regress realized quality on stuff knowable at the time of entry, you can explain about 10% of the variation. Okay, so 10% ain't 0, but it ain't 1, so you're going to end up somewhere in between. So let's order the innovations that we have by their predicted quality at the time of entry, and then let's sum up the D of n. We have something in between, that red thing. How should we extend it? Well, let's fit an exponential to the last 25% of observations, and we can extend it out to here. Okay? So there we go. So that's how we're going to do it, and we're going to use this d hat of n function to solve everything, along with the d for women from removing some women. So the equilibrium welfare effect, we've solved for N1M, and now it's just two different colors in the denominator, right? Fewer or less female value, but potentially more male value. Okay. All right. So what range of possibilities is there here? Well, it's between the naive estimate and 0, right? So it's not guaranteed that there's a value from the female influx, right? So it's going to be an empirical question. All right, so implementation here. What do we need to do here? What we need is sigma. We need the sigma from demand estimation. So we do that. Given sigma, we can get the deltas in the dn function. We're going to do it all separately for patents and articles. Perfect. Separately for patents and articles. And in every case, we'll have estimates for all citers, female citers, and male citers. All right, so if you look at the demand estimates, all I want you to take away here is the sigma parameters showing the substitution are reasonable, between 0 and 1. So that's good news. There is some evidence, again, about the kind of gender homophily here. You see that women cite stuff by, or attach higher utility would be the interpretation in this regression. The column 2 and column 5 are positive, whereas columns 3 and 6 are negative. So women attach higher value to female innovations and men attach lower value to female innovations. The other thing to note is that the articles are closer substitutes for one another than our patents because the sigma parameters up for 1, 2, and 3 are bigger than the sigma parameters for 4, 5, and 6. All right, so on to sort of the answers in some sense. The naive welfare effects, this is just from taking out women but not allowing a male entry response. And so what you get, and remember, these are denominated as percents, like what percent, how much, by what percent is the status quo higher than the counterfactual. And so overall, on the article side, it's like 5.7%. On the patent side, it's 1% or 1.1%. Separately, if you do it for women, it's much bigger. So it's covered up there, but it's like 14% on the article side, and I guess almost 2% on the patent side. And then the male ones tends to be a bit smaller. It's a little bit interesting that they're much closer across gender for patents than they are for articles. In a picture we're not showing you, the gender differences in citing patents are much smaller than the gender differences in citing articles. Maybe the role of patent examiners in disciplining, who knows, but that's kind of interesting. Anyways, we estimate this model a couple of different ways and get these similar kinds of welfare numbers, but these really aren't the main event. These are the naive estimates. So if we allow for the equilibrium responses, everything, of course, gets smaller. The dark bars here are the equilibrium estimates, so instead of 5.3 for articles, the overall is 2.2. The female one's 3.4, the male one's about 2.02. So everything does get smaller with the allowance for a male entry response. But still, it could have been 0, and so the male entry response provides some, but not all of the benefits of the female influxes. The other thing maybe worth noting, there is this literature on kind of direction of inventive activity. There's a little bit of a hint of that here in the sense that different users of innovation are deriving different amounts of benefit from it. It's not by topic, but it probably is underneath it by topic. All right, so we also provide these calculations. There are mind-numbing pictures that I won't show you that show this percent delta in innovator surplus separately by academic field or by patent area. And it's pretty big in some areas, so like 5 to 10% for education, law, psychology, stuff like that. It's bigger for pharma and materials chemistry and food chemistry in patents. But the thing is, those are almost trivially driven by the sizes of the influx. So that's interesting, but it's very retrospective. What we think maybe is a more interesting question is to think of where are there large marginal benefits, right? Because you could have a category that women haven't entered much, but it would be nice to know how much the delta CS, how big is it in relation to how much entry has occurred there. So we do that. This guy's still not working. And so what's kind of cool here, I don't know if you can see us that well, but there are some low influx areas, even STEMI areas on the article side, where there are really high marginal benefits. So stuff like chemistry, medicine, what do you got there? Basic medical science, physics even, okay? So this is really kind of interesting. These are, in the sizes of the influx, these are small, but the marginal benefits are potentially large. And there are some similar things going on in patents as well, okay? So that arguably speaks to the benefit of doing whatever we're doing to continue encouraging influx into these activities. All right, so I'm going to come in, I think, on time. We provide descriptive evidence with some really cool new gender attribution data. I say that because Matt did it. If I did it, it wouldn't be that cool. But it suggests that the female influx is valuable. But then we go beyond the suggestion and provide an equilibrium way to quantify the benefit of the influx. And I think we show that the female influx is valuable, especially to female innovators, but also to male innovators. Now, of course, there are larger total effects in some areas, but I think what's maybe more intriguing is that the marginal benefits are pretty high in other areas, including low influx areas and including things that haven't been traditionally very female involved. And so that suggests, I think, that further inclusive innovation may have substantial benefits. So that's what I got. Thank you.
Thanks. I think the paper nicely illustrates that if we would cut the funding on any studies in gender, we would lose a lot of value. So thanks for showing this here. So we have as the discussant Francesca Truffa from the University of Michigan.
Hi everyone. Thank you so much for the opportunity to discuss this fantastic paper. So the motivation behind this paper is that the share of female innovators dramatically increased in the last decades. And among these women, there are some of the most prominent scientists of the last century. And so this paper asks a very important question, that is, what are the welfare effects of this increase in female representation in innovation? So there are many reasons to like this paper. One of them is definitely the question. So previous studies from people in this room as well documented the increase in female representation in innovation, but we still have limited evidence of the welfare effects of this change. And so the authors address this question using a rich set of data. So they have both academic articles and patents. And with this, first of all, they find 6 important descriptive facts. First of all, what they show is that there is, in fact, a large increase in female representation across all fields in innovation. Second, they show that this innovation is valuable. So like women's innovation receives basically as many citations per innovation as men innovation. And in line with this, the increase in female share in innovation is proportional to the increase in female share in citations. Then they show that there is an expansion of the market, that there is no evidence of displacement of male innovation by the female innovation. And finally, they show that the quality of innovation is really hard to predict at entry. And then they use these facts to inform a structural estimation. So what they do is an equilibrium model of demand and entry with 2 counterfactuals. So first of all, in the first counterfactual, what they do is they reduce female innovation to the pre-1970 level. And then in the second one, they keep the first setting, but they also allow for male entry. And so this allows for some at least partial potential replacement of male innovation for missing female innovation. So what I thought is that this is a very clever and at the same time very tractable adaptation of the Berry model to this context. So to think about this, if we think about a parallel between the two, what we see in the standard Berry model is that we have producers, we have consumers, they choose one product among a set of products. Here in this paper, we have innovators. They choose one citation over the many papers that are already written. The standard model has as outside option don't buy. Here is not citing. Instead of a consumer surplus, we have an innovator surplus. So basically what the model does is to approximate the bibliography formation as a sequence of independent citation choices. So as a researcher, I have to choose my first citation. I'm gonna look at all the papers that have been written. I'm gonna pick one. Then I'm gonna choose the second citation in the same way, looking at all the papers, and I'm gonna pick one. So I think this was very, very clever, and I thought that this was a very intuitive way of thinking about this process. What I would like to see more in the paper is a discussion of the following. So when I think about how researchers make decisions about the bibliography, I think of them as choosing a set of references instead of isolating citations. So like, if I think that my paper is gonna contribute to the event study literature, then I'm gonna cite the set of references on heterogeneous treatment effects. Now, this means that some of the citations are jointly decided. Now, I'm not absolutely advocating for a more complex model here. I think that what helps the reader would be to have a discussion on this and what could be the implications of this, if any, in this case. And I also think that the data can tell us something about these co-citation patterns. The second comment is about a result that I thought was very intuitive. So what they find in the descriptive facts is that female innovations received more citations from women, and that women experience a larger increase in the innovator surplus from the female influx. Now, there may be many reasons why this is the case, but the first one that came to my mind was the fact that male and female researchers may concentrate in different topics within the same field. And in fact, we know from previous studies that male and female researchers typically investigate different topics within a field. And so, again, I think that the authors have all the data to look into this. So, like, one way of doing that is maybe in the MAC data, you can look into subfield levels or even lower levels. An alternative way is to look at distance between innovation from men and women and see similarity and accounting for that. And I think it would be very interesting to see whether this can capture some of the evidence we have here. And third one, and maybe this is more a comment for the next paper that I would really love to see. So in this paper, the value of an innovation is the knowledge that this innovation generates for future innovation. And this is measured through citations. So what I was thinking while reading is that some innovation may generate large social value even if they receive few citations. And this may be even more important when innovations address previously neglected problems. And in this case, there may be a disproportionately larger effect on health and education and inequality, which is not maybe reflected as much in citations. And this may be particularly relevant for women if they study or if they concentrate on understudied topics. And so, for example, we know that the entrance of women in medical science has been linked to breakthroughs in areas related to women's health, but we are not sure whether this was reflected into larger citations. And so I think that a very exciting next question would be to see the welfare contribution of women also incorporating this aspect. I have a more minor comment here, but let me just conclude saying that I hope that it was clear that this is a fantastic paper studying a really, really important question. So I'm really looking forward to read the next iteration of this. Thank you.
So, thanks. So we have our budget in terms of how many minutes we have for a discussion really allows for discussions by whatever gender that you have, female or male. There is no substitution effect, so we can have them all types.
Yep. So if I understood your definition of a female paper, it was 50% of authors. And that definition concerned me a little bit in terms of its ability to compare to other fields where the data is predominantly on first author, senior author, corresponding author, rather than total head count. And so you might need to think about how that might affect your data.
First of all, I just want you to know that this paper is going to be one of the most cited papers in the when thinking about. So you started a whole thing. This is a great paper. I wanted to say that. And second of all, I'm wondering, for all the politicians who say, well, so what's the value of women? If you could somehow put a dollar amount on some of these, we might get a little sense of the value of women. And this is not saying, and women's topics are more important at all. That would be something else. But you could find out the value of women in entering this area.
Thank you. Great paper. I want to emphasize Shu's comment. I think there's an opportunity to look at gendered innovations and gender and health, so emphasizing what Francesca said as well. Londa Scheibinger is a science and technology historian, has a website called Gendered Innovations, and it's case studies of how the crash test dummies were built for men, and women are more likely to get, whiplash in car accidents, for example. And you also have a natural experiment with when Bernadine Healy became head of NIH, she emphasized that we need to include women in clinical trials. And more recently, NIH mandated that you have female mice in experiments because they were only using male mice. And so you have two natural experiments at NIH about women's health that you can use and look at these gendered innovations, because I suspect that the lack of crowd out may be the fact that women are focusing on gendered innovations that is, a whole market that's been ignored. So really great paper, and I think you have another paper where you focus on the gendered innovations.
Yeah, second a lot of those points. I guess I have two questions. So one is, women tend to be credited less on patents than men are, so how do we think about this measure of female patent, male patent, if we're sort of just systematically dropping some people off? And then the second thing is, it may be that the benefits of having more women as patenters may not come from having just a greater supply of female patents, but having more mixed gendered teams and them sort of diversity producing more important patents.
First of all, I share with the room's sentiment about the importance of this paper, but I have some small quibbles. As a female author myself, who often work with the other gender, I want to say two things. Men and women think very differently, and then together we make a paper better. Okay, of course, in this paper it's very difficult to measure the quality of a paper, of a patent, but I think if you eliminate paper, if you eliminate female participation or reduce it to the 1970s level, the world would have changed. In your model, I think there are two things that could have changed. First is that the sigma similarity parameter. This men are great. Maybe they might write papers that are more similar without women. Second, this male's decision to write papers until the benefit equal to the cost, this equation may have to change, because without female partners, the papers, the benefit of papers, the citation they're going to get will be reduced. So I think that to consider that the value of the co-authorship is sort of like missing in this research. Okay, thank you.
So first, I want to know why you didn't use KPSS. No, all kidding aside. What struck me was something Joel didn't say, and I'm wondering if it's something you could have said, which is the following. It seems to me that the fact that the marginal value of female contribution seems to be very high in some fields with low female participation, in the context of your model, implies that the low participation is at least in part the result of some artificial barrier, like discrimination or institutional barriers to women entering the field, rather than, somebody might say it's just women don't want to do that or whatever. And if that is a correct interpretation in the context of your model, maybe you should say that.
Hi, I wanted to ask a bit about how the marginal cost of buying a good may be different from the marginal cost of an additional citation, and how, if we purchase goods, there's kind of a fixed budget constraint, but maybe the budget constraint in this context is time, and maybe the budget constraint on time is not the citing for each paper, but reading the papers across
kind of to expand your knowledge and how it might be a bit different.
I guess I wanted to think just a little bit more about whether there was a difference between the citations to the papers and the patents. Because I guess I feel a little bit worried about this idea that like more citations, either forward or backward citations, is always a good thing, right? I might, like if I'm an inventor, I might really prefer there to be no prior art at all on a particular topic, right? And I might prefer that my patent is so incredibly good that no future people can patent in that area, right? And so that at least is going to push us in the other direction. And so I'd love to hear a little bit more about that. And you might think about doing some measures of patent scope as well. So if you think about what you're measuring is like how dense the patents are in an area by the citations. If you see that the actual size of the contribution in terms of the patent scope is at least as big, I think that would be a nice supporting pack for you.
First and foremost, I would want to say I like this paper a lot. I mean, I have a question. Think of it like a open-ended thought exercise. Imagine if Pete Hackseth were in this room with us, what kind of like policy implications you would want to suggest? Just a thought exercise. Thank you.
Yep.
Well, I think, first of all, thanks are in order.
We have to talk in the mic. Otherwise, for the YouTubers.
Yeah. Okay. You know, first, I just wanted to thank the discussants so much. I think you helped make clear what I've tried to say. So, plus gave us ideas that are actionable and good. I don't really want to respond. I want to mostly just say thank you. I mean, a lot of these things are actionable, though, which is what I appreciate about them. I also want to not forget to give Matt his public service announcement time. Now, how much, if we stay on schedule, how much time do we have? 1.5. 1.5. So why don't you go first?
Okay.
Public service, then maybe I'll say something. But
all right, so every few weeks I get an email from somebody saying, hey, Matt, that citations database from patents to papers is like 3 years out of date, and what's going on? And so I have this like boilerplate, well, the grant ran out, so I don't have time. But then like AI, right? And so when they took the export restrictions off of Fable 5, I was like, Fable, here's this 40,000 lines of Perl code that only runs on like the Cornell distributed computing. Like, can you make it run on my like server under my desk in Python? And it did. So the 2025 data is out as of yesterday. So if you go to relianceonscience.org, it's all up to date. And we fixed a bug because every few months I get an email saying, by the way, where did the in-text citations go for 2022 and 23? So it's all fixed. And so I want to thank Danny Goroff and the Sloan Foundation for the Patents View Plus grant from last year, which made it possible for us to focus on this. But anyway, we're up to date now. So finally.
And so again, so all these are great. We're going to explore them. The one thing about barriers, I like the barrier thing. We had thought about barriers in the past, but you're right. I hadn't thought about, there are implied perhaps barriers in the present that we hadn't thought of trying to infer. But these are all really great, useful comments. So thank you so much.
the Sloan Foundation for many years, and it's a really unique gathering in the sense that we're able to bring together the research community that thinks about the way in which the economics of science works. The Sloan Foundation has also been supporting another activity at the NBER, which is about the financing of higher education. And we've had a conference in the last year and a half organized by Kay Husband-Feeling and John Campbell, which has looked at questions like how do changing endowment returns, how do changing enrollment numbers, how does the role of foreign students in the financing of higher ed in the US work. And one piece of that has been, how does research funding work, but the meeting that we last had was actually before some of the topsy-turvy things which have happened in research funding. So we actually, Danny, this is a no-cost extension to you, but we are hoping to have another conference which will take place in the fall of 2027. And one of the things that, as I've been listening to, and all of you have been hearing some of the things in this meeting, one of the things which, of course, is really important to tackle at the moment is issues around the indirect cost model, the federal financing versus private financing, and individual philanthropy versus institutional philanthropy versus federal funding of scientific inquiry, the role of international financial flows, whether that's private corporations in other countries or foundations elsewhere. So if any of you are thinking about any of those issues, okay, we will push out a call for papers and call for proposals sometime in the next month or so. And it's a long gestation activity. We're not thinking that this is a deliverable until probably October of 2027, which will give us a little bit more time to learn what some of the ramifications have been of the financial shocks that have started in January of 2025. But very interested in this subject, anything from thinking about different indirect cost models and how they might work, to understanding the economics of federal support for capital as well as human activities on the research enterprise, to what's happening as we think about the level of funding for this. And it's not the rate of return to the investment so much, which is of course what a lot of this meeting's been about, but it's rather the bean counting that goes behind this and how we pay for it all that is where we want to be. So we're sort of thinking of this volume that will come up, and this is, Kay and John and I will do this together, as probably having, a third of the volume will be about some of these science funding issues, and then other pieces will be about other parts of the research funding, of the university funding, structure. So thinking about any of this, either grab me, grab Kay, send us an email, and just delighted to have any input or suggestions. And with that, I'll turn it over to our regular scheduled programming. Thank you.
Thank you so much. Okay, we're going to have a bit of an acceleration in the program. So our focus for the rest of the day is AI and science. And we're going to switch to a model where we have 10-minute presentations. And we'll ask you to please hold off on your comments until after all of those lightning round presentations are done. We'll have an opportunity to have a discussion of all of the presentations kind of all together. Then we'll have a short break, and then we'll come back for a panel discussion on the impact of AI, where we'll have some actual practicing scientists on the panel. So hopefully this will be a good session. So I think we're going to start with this Yifan Qian. Okay, so please just take it away whenever you're ready. Thank you.
Test it, okay. Hi everyone, my name is Yifan Chen from Northwestern University. So thanks so much for organizers' opportunity for presenting my journal work with Dasheng Wang and other lab members from our team. So in this paper is actually coming out in PNS probably next week, but I still very welcome all your comments, which I can incorporate into the next work we are working on this line. In this work, we are essentially studying how the rise of AI is reshaping the U.S. federal funding landscape. So on the one hand, we all know that U.S. federal funding play a very important role in shaping the direction, diversity, and impact of U.S. scientific enterprise. And on the other hand, we all know that large language model has been rapidly diffusing into the scientific practice with growing evidence on the use of LLM in preprints and published papers. I show one reference here, actually, the recent science paper published by one of our former colleague, Yan Yin's group from Cornell, document the rise of use of LLM in preprints. but little is very knowing that how the rise of LLM is actually reshaping the U.S. Federal funding landscape. We argue that this gap is very consequential because funding operates upstream of publications, recognition, and promotion. And when there is a gap, there's a reason for a gap, right? In this case, the major reason is actually the data gap. So we all know that the proposal text, especially unfunded grants, are typically confidential data, so making this stage of federal funding very hard to study at scale systematically. So to address this gap in the past years, our team has been working with universities to collect their internal administrative data, including grant proposal, both funded and unfunded data. So this gives us a sort of a unique opportunity to study this question. In this case, we combine two levels of data. So on the one hand, we use confidential grant proposal data from NSF and NIH from two large U.S. R1 universities, including funded, unfunded, and pending proposal, ranging from the year of 21 to 25. On the other hand, we of course can study all the public release awards from NSF and NIH along the same year. So from Dimension database, Dimension also gives us very nice linkage, towards all these resulting publications from these grants. So with this sort of two layer of data source, we can study a series of questions along the public funding, pipeline. First, we can try to understand, how the use of LLM is associated with the kind of idea proposed, right? Then we can also study, whether the use of LLM is associated with proposal success and whether lead to more, research output out of these grants. So before everything, one major task here is we actually need to detect LLM use, in grant abstract. This is a non-trivial task. Here we closely follow the literature along this line. More specifically, we leverage a sort of a distribution level LLM detection framework developed by colleagues from Stanford. Basically, I'm not going into the math here in detail, but to give you a high-level intuition, so basically here we leverage sort of the, compare with human written and, LLM modified text. There are certain words tend to appear more in one direction. So to more specifically here, we leverage all the, public NSF and NIH grants from 2021, which presumably are all human written because this is pre-GPT age. Then we actually use, GPT 3.5 Turbo to actually rewrite those grants by keeping the main idea similar, so we can sort of get two word distribution, one from human written, one from sort of LLM. Then we can sort of leverage mathematical, maximize likelihood optimization, given any new grant or proposal text, especially abstract. Then we can sort of estimate to which extent this grant is modified by LLM. Specifically, we can get alpha out of every grant, sort of to indicate a fraction of sentences are modified by this language model. So just to give a specific example, this is sort of the awarded grants from NSF in 2024. So here you might, here I just highlight a few words which tend to appear more in the sort of LLM modified word distribution. You may recognize some words like delve, potential, endeavor, etc. Right? But this is just one example. So if you look at the whole landscape, right, across both private submission and the public awards, here the first row I'm showing over time, since 23, there is a sharp increase of LLM use across different data sets here. And at the individual level, we can see sort of the distribution followed by bimodal distribution. There is a very large of grants where we detect no LLM use. And again, there is sort of another peak around 10 to 15%, where a lot of LLM has been used sort of around this grant proposal. Again, this is another sort of bird view give idea of how the landscape of funding look like. Here is data correspond to public NSF and NIH in the past years, and I just used the sort of light to highlight higher LLM use, so you can give a sense of this is sort of really spreading out across different sub-agencies and the subfields. Okay, now we have sort of a key independent variable in our study. Then going back to the three questions I listed before, how this sort of LLM use is associated with different outcome here, right? So here we adapt a simple fixed effects regression model, basically by controlling for, funding amount, year, topics, and investigator fixed effects over these grants to study the relationship between LLM use along different outcome here. Of course, Here, the estimation we are exploring within investigator variation. This result should be interpreted as conditional correlations rather than causal estimates. So before I show the results on how LRM related to the, sort of the idea distinctive of the new grants, let's just think through what we might expect, right? So on the one hand, we all know that this LRM can help you quickly sort of explore different topics, and the fields. So on the one hand, it actually can help you sort of navigate the growing burden of knowledge, and actually might help you explore unfamiliar domain more efficiently, right? On the other hand, we all know this LRM actually trained on, funded grants, published scientific papers. So it tend to give sort of high probability typical language that might more align with, prevailing norms in the field. So from this perspective, it might actually push you towards more exploitation, more closer, similar to recent funded ideas. So, which direction are we looking at is actually an empirical question we can test in the data. So in the data, basically to measure the idea distinctive, we just measure the spectral embedding distance between the focal grants versus last year's funded grants to get a sense of how this new grants is sort of similar or dissimilar to the recent funded ideas. In this case, a higher distinctive means that so you are more distinct from the recent funded ideas. So in this case, we find that higher LRM use is associated with lower distinctiveness across both private submissions and public awards to give a sense of the magnitude. So for example, in public NSF awards, so moving from lower NSF, lower LRM use from 25th percentile to higher, let's say 75 percentile correspond to a 5-point decrease in the distinctive percentile. Moving forward, does really use LRM help you, propose to get funded, right? In this case, we look at all these private submissions. So here, interesting, we find, agency-dependent effect. So at NSF, we detect no associations between the LRM use and the funding outcome. But at NIH, we detect, within those investigators, across their proposals, if you use more LRM from lower to higher use, actually associated with 4 percentage points increasing in terms of the funding likelihood. Similarly, when you look at the publication outcome, of course here those are relative early stage of grants, so we can look at the early stage publication outcome. Similarly, we find an agency-dependent effect. There's no association we detect at NSF, but at NIH we do see that from lower use to higher use of LRM, we see more publication coming out of these grants. But when we look at highly cited papers, this effect disappears. It means the productivity gain are more concentrated on non-hit papers. So just to highlight, if you look at the effect size, when we look at the productivity effect here, it's sort of just 5% more papers. So compare with recent study in science when people document using LRM in preprints, where you see like 40 to 60% of productivity increase. This increase is relatively modest, right? So we link this sort of modest effect related to the economic innovation literature, thinking about the bottleneck in terms of finishing tasks. So here, discovery is shaped by multiple frictions, and a lot of these tasks, cannot yet, solved. So I will skip the robust check and skip the limitation. Just to find the key takeaways, this is a figure I like a lot. Basically, a lot of times we are sticking on this text and the sort of predict next token coming out of these grants. To summarize, we do find the LRM use is already reshaping how scientific ideas are articulated and evaluated in the US funding landscape. This finding, I think, with implications for research diversity, transparency, and public trust in the stewardship of taxpayers' supported science. Thanks so much for listening.
Thank you so much, and thank you for sticking to the time.
Yeah,
that
sure,
was great. So next we have Mo Hosseinian, thank you, from Northwestern.
It's not easy. Thank you to all of you. Thanks for the organizers. It's a pleasure to present this work. where we empirically try to understand how AI changes the way that science is organized and how it changes the outcome in terms of productivity, in terms of impact and novelty. So thinking about these questions, an example that comes to mind is AlphaFold, and as specific and unique as it is, I like to use it as an example because it helps me highlight some of the dimensions that I'm trying to get at in this project. So prior to AlphaFold, the protein structure discovery was using a lot of heavy lifting experimentation up front that required pretty expensive equipment, very specialized workforce, and because of the nature of the process, it could take from several months to several years. Now, what you could do with that experimentation now with AlphaFold, you can do with essentially a predictive model. It doesn't mean that the experimentation goes away completely, but it can be pushed back in the pipeline a little bit to just understand what the properties of that predicted structure is relative to your problem. With that, what happens is it changes the mixture of the capital being used, not only the equipment, but also potentially the human capital that goes into it. Now, this seems to generalize beyond just the case of AlphaFold, where AI enters the fray. You have this reorganization of activities, potentially changing the investment in the capital, in the human capital, and the technical capital. That's complementary to this new method of doing things. And potentially there could be this lag. It was interesting to see the productivity results that was presented. And maybe there is, because of this change in the profile of the skills, you might need to organize them also differently. It also changes the calculations of how funding gets distributed, right? Because now you have different set of equipment, potentially different costs associated with these projects. So it might change the way that people engage in these sort of activities, the institutions that might be able to do this sort of research. It might open up some of the funding that now you can invest in studying some of the proteins that you could not have done before. But it also poses a dilemma in the case of social welfare. Which set of proposals do you invest in? Which one maximizes welfare? So it's good to have these ballpark numbers, and that's what we're trying to offer at this point. Without going into the details, essentially I would label a proposal, in this case, AI-driven, if AI is using any part of the pipeline. So we just don't look at the text, we actually look at the raw text and try to extract if AI is being used in any part of the pipeline. I throw away all those cases where it's just a mention of the name. Deep learning has been used for such and such. If that's all the proposal has, that's not going to be labeled AI-driven. For the genuine uses that we can get from the text, we label them AI-driven, and then we make a comparison between conventional and AI-driven proposals across several measures. The likelihood of funding, how much they cost overall, how long they take to complete, the size of the team, and I think my favorite and probably unique thing about this work is I can track how funding gets allocated between different types of capital, and of course, outcomes. All right, so the data is coming from the Novo Nordisk. We have the data for the last decade or so. We have the full text, some really nice metadata, but I think, again, the unique point is that we have budgetary information that will allow me to disentangle and track how funding gets allocated to different types of capital. All right. This is a sort of like idea of the comparison that I want to do. Let me jump into the results. On the outcome front, only for outcome, I have to condition on proposals being accepted because I can then track what sort of papers came out of that proposal. I'm going to present results across several different variables. All of them I'm going to present the slope on a dummy variable that indicates the proposal uses AI or not. Different sort of measurements, different settings tend to produce similar results. So I'm just going to stick with this simple presentation of results. There are a bunch of things controlled for. Let me jump to the result. So similar to the case that Yifan was talking about, we find that the only thing that really changes is the total number of publications. And that's a pretty weak result too. It's like, I think, amounts to 4 extra publications in our case. Interesting in a way, but it's a weak result in a way. On what I call impact, citations tend to go up marginally, but that's not an average effect. It's really the top hit paper that's doing the heavy lifting on that front. The journal impact factor is not really changing. And on the novelty side, it seems the evidence, I'm using the conventionality and atypicality measure, and it seems like the evidence suggests that they're not really mixing with the rest of the crowd. They find their own niches and tend to stick to that, apparently. Okay. Going to the part that I'm a little bit more excited about, on the way, so I'm going to tell you a little bit about the composition of these proposals. So good news is, in terms of funding likelihood, the first result, there's no real difference between the conventional AI-driven proposals. Sort of good news, they're not being funded just because it's this shiny new toy around. In terms of total budget, AI proposals are actually cheaper. That's, again, good news. To my surprise, they take longer to finish, that last set. Sort of expectedly, they are marginally organizing larger teams, and my favorite, the last three, as a total fraction of budget, AI-driven proposals allocate more money on human capital and take away some of the costs from operational and experimental costs. Let me decompose that a little bit. I'm sure you would appreciate that. So if I decompose those three buckets into slightly finer grain, you would see that really the change in the salary side is driving the human capital side up. And what's taken away in the AI-driven proposals is lower operation costs and lower experimental costs. It's sort of consistent with that case of AlphaFold, in a way. You would think that maybe salaries are higher because teams are larger, but if you produce per capita, similar pattern essentially emerges. It seems like PIs are better off in these projects in a way. All right. I have some hint about why these proposals are potentially longer, but it becomes a little speculative. Essentially what I find is, if you look at the tasks that these are doing, unique set of activities that these are doing, AI-driven proposals cover most of what activities are conventional, similarly conventional proposals are doing, and add a computational component to it, which might be okay and understandable in the case because it's the pharmaceutical and healthcare related context. But let me potentially talk about this offline and jump to the conclusion as I'm running out of time a little bit. All right, so to summarize, what we find is AI-driven proposals are almost as likely to be funded, in this case at least. They are cheaper to fund, they're a little longer, take longer to finish, they're organized in larger teams, and again, my favorite, they spend less on capital as a fraction of the budget and more on human capital. Not a lot of stuff are going on in on the outcome side. So the evidence seems to be consistent with this general purpose technology theory, that there is clear evidence of reorganization as far as I'm concerned, but not so much immediate impact. And the question that I have not a good lot to say, but I'm really excited about, is whether this is the new norm, where we just going to invest more in human capital. I'm guessing more likely it's just a transient period. Maybe you can help me understand this a little bit more. It seems like these AI-driven proposals are finding new niches and just sticking to those. They don't really mix with the crowd. There's evidence in the literature on that front as well. And they're organizing larger teams. It seems like, on average, the salaries of PIs and the team members are larger. Now, does it mean that these people are higher skilled? I don't know. Potentially, we have some data to look into that sort of question. And then the one that I'm super excited about, and I think we might be able to get from the research proposal text, is whether teams driving AI-driven proposals are organized differently and coordinated differently in a hierarchical form or more flat sort of organization of teams. Let me leave you with that. Thank you so much.
That was great. Thank you so much. Next, we have Neil Thompson from MIT, who's going to talk about the AI-enabled scientific frontier.
All right, good morning. So this is going to be a sort of a just the facts paper, but it's one that I hope will be very interesting in terms of what it's telling us about AI and the scientific frontier. And in particular, I think it's going to contribute to sort of two things. So one is, there's this discussion going on right now, which is like, there's this sort of terrible version of AI, which Eric Brynjolfsson has called the Turing trap, where you say, like, human used to do this, I'm going to replace it with AI that kind of performs about the similar way. And it's like, well, we didn't get much more out of it, right? We just substituted it out, a human became less well off, and that doesn't seem like a great outcome, right? And I'm going to show you a very different kind of AI improvement today. I'm going to talk about how AI is making tasks that are done by computers better, okay? So this is as far from the Turing trap as you can get, right? Because there's the tools getting better. It also contributes to literature. There's this sort of discussion about, like, is AI just, like, better than other techniques that we've had in the past, right? And, Pedro is more sort of making an argument about, like, in the future, we might be able to do more things, but some people are sort of already making this argument today, that AI is going to push these things forward. This is just better on all of these fronts. And we want to take a bit of a skeptical eye to that and say, well, is AI a better algorithm, or is it just a different algorithm, right? And if it's a different algorithm, we might expect there to be lots of economic trade-offs of the kind that we're very used to thinking about. Okay, all right, so as we think about this, we're going to want to separate out what AI is doing by, in this case, what we're going to call the sort of scientific frontier of analysis. So on the left-hand side, you can think of traditional statistics. This is like the stuff that we do, right? We write down a model, we say, I want to estimate that. It costs, less than a penny to do most of the stuff that we're doing. We heard some exceptions yesterday of people like burning up, but generally incredibly cheap to do this. At the other extreme, we have like weather simulations. Okay, weather simulations cost about $4,000 every time you run them. Okay, this is huge amount of compute. And of course, this is, I'm going to think about the amount of compute that's involved here, because as you scale up that compute, you also scale up the cost, right? I think we're all a lot more familiar with that in the era of AI than we were before, but this really matters a lot to this. Okay, so if that's the sort of frontier we have, we're going to think about, well, how does AI change that? And the way we're going to do that is we're going to find 2,507 different comparisons in the literature where someone said, hey, I went out there and I tried to use AI for this technique, and I compared it, and I say, like, this technique was better. So you get things like this, right? So this is a PNAS paper from 2021, Machine Learning Accelerated Computational Fluid Dynamics, and their conclusion, as accurate as, the AI version is as accurate as base solvers with 8 to 10x finer resolution in each spatial dimension, resulting in a 40 to 80-fold computational speed up, right? Which of course, as we just said, that would be like 40 to 80-fold cheaper in order to do that. That would be a really big deal in order to do these things. So we go and we find these. This is hundreds of papers, many of which have multiple comparisons across them. And what we want to do is we want to categorize them in the following way. Okay, so on the horizontal here, we have whether the result is you get worse performance or better performance. And on the vertical here, you have whether it's lower cost or higher cost, right? So if the AI is just better, crowd is right, we should see a whole bunch in this category here, the win-win, right? Better performance, lower cost, that's pretty great for science, right? If this is more of a different algorithm, we're going to see more in the blue or in the yellow, right? So the blue here is efficiency prioritization, right? My result is not as good, but I save a lot of money in running it. That could be useful for some people, right? And in the gold here, performance prioritization, I'm willing to pay more to get better performance on it, okay? Now, importantly here, right, there is some selection that goes into what articles people actually publish, right? Now, you might say that's going to sort of bias us into these three categories. Maybe. I would say, like, having sort of dug into this a little bit, there are also lots of people who pride themselves on writing the article that is like, hey, you think AI is great, actually this technique that I pioneered is actually even better, right? And so there's a lot of stuff where it's going the other direction as well. Okay. So we want to hypothesize, right, that if this is more like a different algorithm rather than just a better algorithm, what it might be doing is still something pretty valuable for science. Right, so here what I've just done is said, okay, let's take that traditional statistics we talked about, which has low computational cost, but also less performance, right? And we want to compare that to scientific computing with a very high performance and low computational cost, and that we sort of, before maybe had to choose more, like whether we were in one camp or another, right? And you really do see that, right? I mean, if you think about like fields sort of divide by the people who are like, I'm doing incredibly big simulations, and people who are like, no, I do reduced form stuff. And there's some skepticism on both sides of that, right? So, okay, so you sort of push in those different directions. And as I showed you before, there can easily be orders and orders of magnitude of cost difference in the actual systems that you're using to do this. Okay, so this is our hypothesis. AI is going to sit up here, and it's going to provide a way to get at some intermediate cost some things. This, of course, implies that we're going to see different effects, right? For traditional statistics, we're going to see people moving to higher cost and better performance, for scientific computing to lower cost but also lower performance. Okay. So let's actually look at this. We'll start with traditional statistics. People more like us, right? So if you go from traditional statistics to AI, what does that move get you? Right? Each one of these small arrows represents one of the comparisons that people made, and the brighter arrow is the net average of all of those things. Okay? And so you can see that you are getting, in fact, it's pricier, but better performance. And in fact, if you analyze this, you get about 23% better performance at the cost of about 10x more compute. Right? I bet you a lot of people in this room can identify with this, of like, we start to use AI for some of these things, and we're like, oh, now I have to start paying attention a little bit to who has the GPUs and how I get a few more of them, right? Okay, so that's this side of things. What about the scientific computing folks? Boy, does that look different. Okay, so again, the lighter lines are the individual papers, and the dark line is the average of all of those. And you can see that, so actually on average, the relative performance is almost identical, right? But we are reducing the cost by quite a bit. And in fact, if you think about this, you get about 284x lower costs, right? So if you go and talk to people in weather simulation or other periods, they are incredibly excited about what AI can do in these areas, because what it's really telling you is like, hey, I used to have to run this incredibly expensive model that limited the experimentation I could do, the number of scenarios I could do, the sort of number of repetitions I could do. I don't have to do that as much anymore because I now have this dramatically lower cost for running it. Okay, all right, and interestingly, you do see that there are a fair bit on both sides of this line. So there are some things where it's just better, right, and some things where you see efficiency prioritization. Okay, so interestingly, there's lots of variation across different disciplines here. So you can see that in some areas, so for example, in engineering, right, actually 40% of the time when you move to AI, it's worse and more expensive, okay? This is, at least from some of the engineers I've talked to about this may make sense because we actually have really good senses of like what a car looks like, as an example, right? And so if you're doing like image recognition on a car, you don't actually maybe need all of the machinery of like a computer vision system in AI. You can actually do it with a sort of a more simple system that actually takes advantage of the things you actually know. You also see, for example, in some places, like lots and lots of cases where performance prioritization is going on, where people are saying, I can do more. But it is interesting, like in life sciences, for example, there are very few cases where it is actually both better and cheaper in order to run this. Okay, so I think I must be coming to the end of my time. I am. Let me just say a few more things about how this is evolving, right? So this is evolving over time, right? And what you can see here is, interestingly, it is not that, for example, when we think of traditional statistics moving to AI, that like, oh yes, but as these AI models get better, it's just all the cases where like it's lose-lose moving to AI disappear. Like it's gone down, but it's actually been stable now for about a decade, right? And similarly, pretty stable at the bottom side. So this is a pretty comparable picture. Pretty different on the scientific computing side here. Here we really do see this trend which says, these AI models are getting increasingly win-win, right? That makes sense because they're getting better, and we're also getting much better at the algorithms and the hardware. In this case, particularly the algorithms, that's making them more efficient. So that makes it much more attractive. You can see the proportional decrease in this. Still some cases where it's loses. Okay, so what does that mean if we actually want to quantify what this AI-enabled scientific frontier looks like? So we can see that our hypothesis is not quite right? There definitely is this relationship between traditional statistics and AI that involves trade-offs, right? You pay more, but you get better performance. But the one between scientific computing and AI, if anything, it looks a little bit like AI is just better than scientific computing. Now, that's hiding a whole bunch of heterogeneity there, right? In some cases, there is the same trade-off, right? But scientific computing is the more accurate one, and AI is a little bit less accurate. In some cases, AI is just the better one. And so this sort of suggests that we should expect certain parts of the scientific literature to be evolving more quickly. Okay, and I won't show this here today, but just to highlight, you can also, interestingly with our data, look at how each of these techniques is changing over time. So people are coming up with better ways to do traditional statistics and scientific computing and these things, and all of them are moving out in the same directions, and so you can see that this scientific frontier of analysis is actually growing in very interesting ways. Okay, and I will stop there. Thank you.
That was great. Thank you so much. So I think we have time for some comments and questions if people want to go to the mic. So I'll start. I had a question for Mo, and that was about whether you looked at, where is Mo? Oh, there you go. Hi. I was curious if you ever looked at interdisciplinarity or collaboration across disciplinary boundaries. And whether you think that the larger team size have higher coordination costs and what the implications of that might be. Maybe you could come to the mic if you don't mind. Sorry.
Roles are reversed. So is this on? Yes. The coordination cost, I would love to get evidence on that. Speculating on it, yes, they should be. They seem to be more diverse because you would need to have the domain savvy individuals and also computational individuals. Now, which part of, if you could think about a team and a hierarchy, which part of the hierarchy gets the computational piece and which one gets the savvy part, that's interesting to see. I think that's probably the easiest to get from the data. But I've also tried and so far failed in getting more evidence about like how much of a hierarchy, evidence of hierarchy there is in the like supervision versus collaboration in the proposal text. I would love to have more answers on that. On the interdisciplinary side, I think we're defining another project where we start looking into the patterns of individual work, like individuals involved in these work, looking at their CVs potentially and their network. Hopefully I can share more of that on the front. Did I miss anything?
I also have a question for Mo. Have you thought about the indigeneity of using AI? You know, because a lot of the things might be that there's just different types of researchers early adopting AI, and I don't know whether you can do something about it, but.
So I had some information on the demographics of the adopters that I had to throw away because of the time. We have a preprint that's included there. We know that they're primarily male, they're younger, but compared to other peers, they're more established in terms of the number of papers that they have pre-submitting the proposals. Heterogeneity across fields, there is some, but because of the data we have, it's still relative to the size of the scientific universe is relatively small. We have data from a university also that spans NIH and NSF. We're waiting on the budgetary information to come through, and then I can hopefully replicate this with those, and maybe I can give you more on that front because then it diversifies a little bit.
Can I just say that NIH and NSF know that NIH a big effect? That tells you a lot about the fields and the reviewers.
So maybe I repeat for the YouTubers whether there is a difference between NIH and NSF, right? Yes.
Okay.
Yeah, just for the
Well, I think that's your territory.
Yeah, that's a great comment. That's the question I spend most time addressing reviewer comment. Indeed, this is a great question. We all know NSF and NIH, of course, by definition, they represent, feature different scientific field, right? So presumably, there are, of course, a field effect there. But to rule out, it's not just a simply field effect. So we actually look at the most common large field biomedical research, because NSF also found some biology along this line. So even there, within biomedical, the common large field, we still see results that are robust. So overall, this suggests it's potentially a combination of field plus some agency-specific institutional effect, right? For example, there are certain review typical process associated with NIH, which is not in NSF. So hopefully this is addressed your question. Thank you so much.
So I have a question for Neil. So you know the publications that are using these different types of, does it, the way in which you use it and how, whether it's lower cost, more efficiency, would that also affect the impact of that research in terms of how much this will then actually get cited and taken up by others or not?
So if I understand the question, it's the sort of an implication of what we find amongst these like 2,500 comparison papers is that, for example, for scientific computing, it's way more efficient. You could ask the question if you then went to the rest of the literature and you said, for the scientific computing that is using AI and therefore should be much cheaper, is it having, for example, maybe much more spread out effects? So people are now running on their own. Yeah, so I strongly suspect that's true, but we can't actually see it from particularly in our set. But I absolutely would believe that that would be true. Yeah.
So for the first paper, my understanding is you're relying on AI detection, which I think in other people's experience, like my sort of gathering of the world has been notoriously bad. And so actually, like I'm curious what you've done to validate that your AI detection is good. And then a comment, I think, for all of these papers, as well as anyone else working on AI, is I feel like there are, you know, a lot of things bundled under AI, right? Sometimes we specifically go after AlphaFold. Sometimes we specifically talk about LLMs. Sometimes when we're talking about LLMs, we're talking about a web browser interface versus like a codex interface. And I think those details matter in what we find, and I would just want to encourage all these authors and also the other people working on AI to be really particular about what tool you're using, because I think we're going to find that the different tools have different impacts, and so I think that's something we need to know as a community.
I think that's very important. So we try to be very, so again, in the part that I'm presenting, I'm only focusing on what we call AI. We try to be very specific about, I think we find 4 general categories in the paper that we discuss, and they have different effects. So that's a great point. But there is having to deal with this and like painting, just like a lot of pain, to differentiate these things. It would be great to come up with like on the research front, it would be great to have taxonomies where we can potentially, you know, from a bottom-up perspective, come up with categories of algorithms. I know it's hard, not maybe a lot of reward in doing that, but for the research in the field, I think that would be very, very productive if we can come up with taxonomies. Could be a project, I think, but not an easy one. So I totally take your point on that.
Interesting papers. Neil, I really like that you pay so much attention to cost. I think everybody else always talks about performance. I think this is really important. And I do wonder, who is the agent making those decisions on whether to push the cost or the performance frontier, so to speak, right? I mean, I read in the papers that Google is trying to figure out how can we make our big LLMs more efficient because we want to use less chips. So there's a kind of very fundamental upstream supplier. It could be a scientist who just has, you know, ChatGPT and says, oh, I want to use it for this, or I want to do that, or I want to use a cheap model, or I want to use an expensive model. Or it could be somewhere in the middle where scientists are programming their own LLMs or training it in certain ways. So I think it would really be interesting because you have it, I guess, in the papers. They describe what they're using and what specific technology to tell us more about how AI evolves. And because which boundaries is AI pushing is, again, is it the cost and performance boundary? And even though we all pay attention so much to performance, someone else doesn't, and that's really interesting. So I think there's a much more general paper potentially here, and I'm curious what you do there or can do there.
So this is music to my ears, because this is a big part of what my lab studies, right? So we're very, very, very interested in this question. So I would say, like, there is a wide menu that is being created. So one of the sort of facts about these AI models is that there are scaling laws in them, meaning that you can almost always trade off more compute for better performance in lots of different areas. And so that can get very expensive if you do it. What we actually see is that if you look at how models are getting better over time, it is dominated by people building larger models. That's really frontier. Comes from building the model bigger. That's really why we think about this comparison as so central, because you actually do scale up your compute a lot to do it. When you look at tasks that have sort of already been done, right? So it's like, oh, you know, GPT-4 could already do this. and then you say, well, how does it evolve over time? It actually gets dramatically less expensive because of algorithmic progress that goes on. And so people may have heard of like distillation and other techniques that are used in order to build smaller models that can do the same thing. And so there it's actually much more algorithmic progress that is driving costs down. And you see both effects going on. I think what that means in terms of the scientists using these techniques is that you should think of this as increasingly being a portfolio, right, where you have different points on the cost performance curve and you get to pick amongst them. And so, you know, I sort of hinted it at the very end there, but you can actually plot sort of as people say, oh, well, I used AI before to do this, but now I'm going to spend more and get better performance, and how that's changing, for example.
Just quickly follow up. So that's an interesting version where it's an existing portfolio and scientists pick performance cost combinations. Yeah. I was thinking someone is developing these performance cost combinations in the first place, and it would be interesting to say which one is it, and is not the development of AI also still responding to the demand, so to speak, right? I mean, is Google pushing the cheaper development or cheaper models, or is it pushing the higher performance models based on what they're seeing developing? It's not this paper, but I think it's really interesting.
Yeah, so 10-second answer, which is just if you can build the really big one, it is relatively inexpensive to build the smaller, cheaper ones from it. And so that question ultimately goes down to like how fast people are pushing the frontier, because you can almost always build a portfolio to follow.
Okay, one last comment. Thank you.
Thank you, Jerry. I also have a comment on most things, because I write the paper on AlphaFold and suggest that it's a different thing from you're saying people pushing more towards the human capital investment. In my case, is that actually capital is the problem here. Those people who have tools, those expensive cryo-EM methods, who are able to solve the proteins which are harder to predict, are actually thriving after AlphaFold's shock. So I think maybe to think about the different infrastructures, how they interact with the AI is very important, because these kind are the things invested at the universities are kind of stable, and even if AI hits the ground, people still need to do the experiments to validate what the AI has to say, and that's something kind of stable, because AI's models ability may change every 6 months, but not for the infrastructures investments in the universities. They're kind of the long-term thing.
Great, thank you. If it's quick, sure.
So I just wanted to point out that what we find doesn't necessarily suggest that the bottleneck is the human capital side. I think what I find in the proposals that a large portion of them, they hire these people to then develop models, but then the per project cost of infrastructure and operation is just lower compared to the experimental projects that are doing the conventional things in a way. I think that's my explanation on what we find.
Thank you so much. And I think we can continue the discussion on this topic when we come back for our panel. Let's just take a super quick 10-minute break, a bio break, and then we will have our excellent panel for the final thing. panel of practitioners, and we have a Jay, who, among many other things, has recently written a chapter for a conference volume that we put together on the economics of science last year. He's going to talk a little bit, giving us an overview about AI and science, and then we have some practitioner perspectives. So, Ajay, thank you so much for doing this, and please take it away whenever you're ready.
Great. All right. Well, thanks very much, right now. And Megan, for putting this together. This is going to be, I think, a real treat for us because we're going to hear from the people who are actually right at the frontier of applying machine intelligence to scientific discovery. The reason I think we care so much about, we're interested in science and the knowledge production function, but of all the things people talk about, AI and autonomous driving and AI and medical diagnostics and AI and language generation, all of those will generate various productivity gains, but nothing will hit economic growth like the impact of AI in the creation of ideas. So I think the reason we care so much about this, and in some respects more than any other topic area, the role of AI and how it may impact the knowledge production function is the most significant with respect to growth. Now, in the context of growth, there are very different views. Sort of at extreme ends, Daron's taken a view that the impact of AI on growth is potentially very limited. And he says more modest increase in total factor productivity and GDP in the next 10 years, upper bounded by 0.5% and 0.9% respectively. And on the other end of the spectrum, Chad Jones, who argues that the impact could be very big. Acceleration of economic growth to some rate, G, perhaps 10% per year. He's not saying it's 10%, but he entertains the idea it could be something like 10%. Now, how do Daron and Chad, who are both steeped in the literature on economic growth, come up with such different views on the potential impact of AI and growth? The answer is they have different views on science. That Daron says, I do not discuss how AI can have revolutionary effects by changing the process of science, because large-scale advances of this sort do not seem likely within the 10-year time frame, and many current discussions focus on automation and task completion. Whereas Chad says it seems likely that AI will augment our abilities to innovate in the near term. And it is certainly within the realm of possibility that AI could match or even exceed human intelligence at many cognitive tasks and begin innovating itself. Once machines can produce ideas, the limits to growth set by quantity and quality of researchers may no longer hold. Okay, so that is the core of how they arrive at such extremely different views on growth. Now, the people actually building these, like the foundation models, they're of course much more in the camp of Chad Jones. Like Dario of Anthropic, my basic prediction is that AI-enabled biology and medicine will allow us to compress the progress that human biologists would have achieved over the next 50 to 100 years into 5 to 10 years. So, in our world, in our production functions, we have capital and labor and ideas, A. And A, the growth in A is a function of the stock of ideas and the number of scientists, and omega, the productivity of science. And so in this chapter that Megan referenced, we decompose omega into productivity of different steps in the scientific process. So the productivity of hypothesis generation, the productivity of idea generation. So you think of ideas as concepts for how you might test the hypotheses. And then productivity in design generation. So going from concepts, design means like down to experimental design. And then productivity in testing. So testing whatever those experiments are. And so the reason we think of this as useful is because there are different modalities of machine intelligence being applied in the different parts of the workflow. Okay, I'm not sure what just happened there. Okay, so In the idea generation, we have, for example, in our field, Sendel has written a couple of papers, one of which was machine learning for hypothesis generation, where he starts with this remarkable fact that so roughly 50% predictive power in who a judge will grant bail to based only on the photograph. So he starts with this remarkable just fact, and the question is, what is the neural net finding in the pixels of the picture that predict what a judge will do, either grant bail or not grant bail? And so the neural net's found something, it's unobservable to us, but they figure out, no, perfect,
Which
thanks.
slides?
Yep, this one. And what they do is they take this latent variable and turn the knob up and down to its extremes, and then morph the picture to generate what does this face look like at the extreme value of this latent variable on both ends. And then put this series of faces in front of human observers and say, what's different about each of these faces? And they come up with, just people looking at the pairs of faces, the two most common are fat-faced and clean-shaven. And so the point is that the AI has produced hypotheses. Like, this is hypothesis generation. And then in another paper, they look at using prediction models to predict anomalies to theories. And the point there being is anomaly identification is a central method for generating ideas for new theory development. So their point is machine intelligence, people saying, oh, machines, like the AIs are just regurgitating things we already know, and they're giving us examples where AIs can be used in the creative process of hypothesis generation. Same in idea generation. I was just over in the other room listening to papers in terms of the use of, for example, the language models in idea generation, then creatively, design generation. At the core of this, in the Romer model, is ideas, and we model the ideas as recombining existing ideas. And the reason that's so important, everybody's in this room is familiar with combinatorics, but just as a reminder, like if we have 25 ideas that we're recombining, and we get one new idea, a 26th idea, well, that adds another 30 million possibilities. It's just like, I find it useful just to remind myself from time to time the power of combinatorics. Okay, so in other words, and the reason this matters so much in terms of AI and scientific discovery is because this becomes the search space. So when we are looking to recombine ideas, we are now moved from a search space. When we've added one new idea to our stock of ideas, we've added 30 million more things to search. And so probably the domain in science that has gotten so far the most impact and recognition in terms of influence from AI has been in this part, the design part. AlphaFold is an example of that. And so they've laid out this characterization of what are the scientific problems that lend themselves to machine intelligence. They have these three characteristics. One, a combinatorial search space that's too large for people. Two is a clear objective, so it's very well-defined output in terms of what's the research question. And three, sufficient data. And with those three ingredients, that set of scientific problems lend themselves to machine intelligence. And then, of course, testing. And you're going to hear today from some of this is a picture from Itinerary, one of the speakers, but many are using robotics and AI control systems in robotics in order to actually run the experiments. So in each of these areas, producing hypotheses, generating ideas, then generating experimental designs, and then testing, there are AI implementations in each part of the workflow. But a number of people have written, but Ben Jones, I think, has sort of has best crystallized the tempering of our enthusiasm because of bottlenecks. And his point is that it doesn't matter how fantastically productive one step in the process is if everything gets bottlenecked in the next step. And so he has this come here, while much remains to be learned, existing evidence and observations suggest that bottlenecks are common in R&D. This means taking over a large share of research tasks, which is how AI can overcome bottlenecks, is likely much more important than radical improvements at a narrower set of tasks. So what I'm going to encourage you to listen to our panel today, and this is why we're so lucky, because we're having non-economists, people who are actually doing the science, explain to us where they are seeing massive lifts in productivity because of deploying machine intelligence to parts of the scientific workflow, and at the same time they'll tell us where there's bottlenecks. So I won't introduce the speakers because I've written little intros here, and just we'll jump right into it, and Keith, offer you to kick us off.
All right, well, thank you very much for the introduction and for the invitation to be here. I think the last time I was in a room with this many economists was microeconomics as in undergrad. So, and I think half of the people in that room quit the field, myself included. I'm Keith Brown. I'm at Boston University. I'm an associate professor of mechanical engineering, physics, and material science and engineering. I also serve as the division head for material science and engineering. I started my group at BU in 2015, and we build tools for physical experimentation. Back at that time, we thought of it as automation. How do we do research faster, more intelligently? And more, once the term was coined, we felt we were doing self-driving labs, which is something you'll hear a lot about from other speakers as well. And these are systems where you have a robotic system that's doing experiments and it's guided by AI or machine learning. Our work, we're best known for early work in the area of 3D printing and polymers. If you're interested to tell you about our domain, we also look at things like formulations and metal organic frameworks and all sorts of fun buzzwords that you're happy to talk about afterwards. The one thing I'll say kind of by way of how I think about the field is back when I started in this, we thought of AI and automation as kind of being equal hand in hand. You had better brains to choose better experiments and better hands to carry them out more rapidly. And I think the tone, the message has changed in recent years to now the idea is, well, AI can do just about everything except physical experiments. And so we need automation to catch up. So it's less of a equal partnership and more of this is a tool we need to augment our AI. And just to show you a bit of the recent investment that you've probably seen all these announcements of the DOE and NSF investments. There's now they just invested $400 million to open basically 20 major self-driving lab clusters around the United States. And so we'll be working at BU to work on one as part of there in biomaterials. And so to ask questions about where AI is, where is it impacting our workflows, it's really in everything from you listed a bunch of different categories, ideation, analysis, right? It's in all of those pieces. I think the bottleneck really is data, in data that is novel, that is not in the training set. And so to us, that means physical experiments. And so that's why we're continuing to push in that direction. Thanks, and I'm looking forward to the Q&A.
Okay, great, thank you. And maybe you could slide down so that people can...
Sorry, we were just in the projector.
Yeah, no, it's good.
All right, sliding down was more difficult than I thought it was going to be. But so I'm Diane Joseph McCarthy. I'm the Executive Director of a Bioengineering Technology and Entrepreneurship Center at BU, and also a faculty member in biomedical engineering. And I was in industry for a long time, in the pharmaceutical industry and biotech industry, before I came back to academics about 6.5 years ago. And so my research is very different from the other panelists, in that it's focused on developing new computational approaches for drug discovery applications by combining physics-based approaches with AI and machine learning. And so I was going to comment on the influence of AI on the biotech and pharmaceutical sector and my field overall. And when I was thinking about that, I decided to break it down into the different stages of the drug discovery process, because the drug discovery process overall has traditionally been very expensive, very slow, and low and really high attrition. So so the use of AI at every stage is increasing at a phenomenal rate, and that's because the hope it will overall increase the rate of drug discovery. So the first step is target evaluation. that's where you're trying to decide which, say, protein, for example, are you going to try to go after as the target. And so there, and you're trying to, say, design an inhibitor for the protein, which would then have the desired therapeutic effect. And so there we heard of a number of speakers have mentioned AlphaFold, and that really has been a revolutionary advance in our ability to predict protein structure, as evidenced by the fact that the Nobel Prize in Chemistry in 2024 was awarded for AlphaFold and for protein design. It's a neural network-based model, and so, you know, people are trying to figure out how to use that model. So some of my work that my group has done is trying to understand, are those models accurate enough to be used for drug discovery tasks? And so I think there's still a lot of work to be done there. We see that the models are sometimes not generalizable to new proteins. And so I've looked at using these models for hotspot mapping to find kind of new binding sites on proteins, for docking to AlphaFold models versus co-folding the ligand with the protein. We've developed an antibody-specific large language model. So that's the other area where there have been very significant advances in protein language models like ESM2, ESM3, ESMC. And so we're all familiar with ChatGPT, where there, you know, you can mask a word, and the model has been trained on the very large corpora of all text, and it can predict what that word would be. And in protein language models, the words are amino acids, so it can predict what the amino acids should be. So then the next stage is lead generation. I think I just swallowed a bug, actually. But, and there are a number of generative AI approaches that are used to create small molecules that are likely to bind to a given target. And one of those is, for example, Reinvent4, which is an open source model, that approach that's come out of AstraZeneca. Then there are also a number of approaches used to design novel biologic therapeutics, right? So RF diffusion, which is Rosetta Fold diffusion, designs new protein structures using a number of different constraints. These are all AI-based approaches. Protein MPNN designs amino acid sequences for a given protein background. So you can think of RF diffusion as designing the shape of the protein, and then the protein MNN designing the sequences that fit that shape. And so they're often used together. And in my group, as I said, we developed an antibody-specific protein language model by fine-tuning existing protein language models on millions of antibody sequences. And we're using that model to predict optimal sequences, and then we are confirming the fold of those antibodies, or in some cases, smaller antibody-like constructs using AlphaFold. The next stage is lead optimization, where you can look at things like there are a number of groups trying to, what you're typically doing in that stage is trying to optimize other properties that are important, like bioavailability, PK, tox, while maintaining or still improving your potency. And so there's something called OpenADMET, which is generating very high quality data sets, again, because the data sets really are the bottleneck. And then they're setting up these kind of blind challenges where people test their foundational models on those data sets. And then there's Lilly TuneLab, which is a collaborative AI platform that Lilly has put out there, where you have access to AI and machine learning models that were trained on Lilly's data sets, data that they've had for decades. And it's a federated learning model, and members can join the collaborative if they contribute a certain number of data points to the data set. And then preclinical, there we have the FDA Modernization Act, which is trying to reduce the number of animals that are used for testing. And so it's emphasizing new approach methodologies, so NAMs, which are innovative ways and strategies to assess the safety, efficacy, and quality of drugs. And you know, so these can be 3D organoids, organ on a chip, or they can be AI, ML simulations, algorithms, digital twin simulations, computational toxicology. And the idea is that predicting human outcomes from really high quality human in vitro data should be better than predicting it from animal studies, and more cost effective. Then clinical trials, people are using large language models for developing study protocols. The FDA is piloting using these models to review the protocols and to, standardize evaluations. And big companies are all developing AI agents for clinical trial design that include the use of ML models for looking at electronic health records, past trial data, to score patients for trial suitability and also for site selection. But I think for all of those, the success, at least now and in the foreseeable future, is really to keep a human in the loop so that there is someone reviewing the output from the AI model at every stage and iteratively giving feedback. And also, the companies are, I'm almost done, developing AI agents as well for computer intelligence, competitive intelligence all across the discovery chain. And for example, we used ChatGPT to, we developed a method that uses it to dramatically reduce the number of time it takes to identify a drug target or a potential drug target from the literature. Also, Claude Code has really dramatically changed the field in the last 9 months or less than a year, because it really enables you to interact with AI and use your computers in a way that are safe and effective, and it significantly advanced the development of the framework really needed to use AI, and so people can code things much more quickly than ever before.
Excellent, thank you. Herman.
Thank you very much, Ajay, and the organizers. Wonderful event. I'm Herman Tribukait. I'm a co-founder and CEO of a deep tech startup company doing AI for science. And I'm based in Palo Alto, California, with most of my colleagues based in Switzerland, in Lausanne, and we just opened our self-driving lab here in Seaport that you saw a picture of. So I want to tell you about actual results that we have, but if I may make it quickly, a quick question to make it interactive, can you please raise your hand if you have been on a Waymo or maybe on a Tesla driving on self-driving mode? Okay, less than, that's like 1/4 of the audience. So what we do is essentially enable Waymos for scientists in research labs. Okay, so we augment humans conducting scientific experiments, and like augment, not replace, humans with AI, and then we can discuss what that means exactly, but a flavor of AIs with robots to accelerate scientific research. And the ultimate goal is to come up with new molecules, new materials, exponentially faster, get them into the market much faster. And what I'm here to say is that this is ready. This is happening today. And that was part of the reason why we decided to actually build, not only enable self-driving labs for our clients, but actually build one and show it to the world. And it's right here in Seaport. And this is a paradigm change, right? So this augmentation of humans allows to free time of scientists instead of spending most of their time in non-scientific tasks, like setting up things, manually running experiments, counting drops, like pipetting, and typing in the data, moving trays from one place to another. So all of that these are part of the bottlenecks, but also the bottleneck is not only on the manual, mechanical, repetitive, and boring tasks, and that are also error-prone, but also on the mind. Being able to solve much more harder problems, like here in this audience, you would probably relate to this if you're able to solve a much more complex optimization problem with many more input variables and many more parameters, and solving or screening a much larger combinatorial space. It's a search problem that these tools allow you. So the bottleneck is not only, again, the hands, but it's also the mind. And with these tools, you can we'll show you how that we can augment this. And I'm also here to say that this has happened already before. We have seen this in genomics. The cost of the cost of sequencing the first human genome in 2001 was about $100 million. $100 million. Today is, I think, approaching $100, if not already less than 100 million, less than 100. So we can do this, and our goal is to do this across the board, not only like this type of acceleration, this type of exponential improvement across the board, right? And for, I was discussing with some of you here in the audience, we all know about Moore's law and exponential improvement. If you write Moore backwards, have you heard about the Eroom's law? An exponential decline in productivity, in R&D productivity, or in the cost of bringing drugs to market. So we want to reverse the Eroom's law to really move from an exponential decline in productivity or in the cost to actually an exponential improvement like we saw in genomics. And just to conclude, I wanted to share with you some actual results from clients, from leading industry companies that are achieving this today. In fact, we published a peer-reviewed article with a leading special chemicals company where we showed that we were able to improve one of the performance metrics by 30 times, lowered the cost by 97%, cut the time of experiments by 50%, all of this in a matter of 1 month. So the combinatorial space in that case was 2.9 billion possible combinations. And this was, by the way, without using robots. This was only applying the algorithms with only, so what the way we work is with this iterative loop. So we run a set of experiments to get the data, which is key, the actual experimental data, what we call the ground truth. What happens, what does nature actually tell you once you run the experiment? So we run experiments, we get their output, retrain the algorithms, and then the algorithms suggest the next round of iterations to run. And so with 22 iterations of just 4 experiments, so 88 observations in a combinatorial space of 2.9 billion combination possible, we got these results. So this is just, again, an example. And if I may finish with a testimonial from a big pharma that we all have tried, we all have heard about them, we all know, have probably used their medicines. This is, again, verbatim, they said, within 3 weeks of running our first campaign on Itinerary's AI platform, searching a high-dimensional reaction space, we identified a candidate reagent that was both higher performing and greener than our benchmark. And here's the most interesting part to me. It says, interestingly, this condition surprised our chemists of a top big pharma, surprised our chemists, and we would not have found it without this technology. So this opens up, again, being able to solve problems that you would otherwise not even attempt to solve. And I finish with this other testimonial from a chemical and food industry company. We are getting a new formulation that is completely different from what we were expecting. If it proves right, this new formulation is going to be a game changer for us in terms of everything. The new compound shows higher performance on various metrics and surprisingly low cost that we did not expect. Itinerary opens up a window of opportunity that is, well, it's a new world. So these are the statements from large companies. And I asked them, so how much better is this compared to standard methods? And the answer, and I finish with this, from the users here, from the scientists, is that I think we cannot compare it because we normally only work with 2 variables. They can only, again, going back to the bottleneck, we only work with 2 variables. With this platform, we're now testing 11 variables at once. How do we test 11 ingredients with the standard methodology design of experiment? That you cannot, it's just untractable. And that would have taken us months and months or years, and it's not comparable. So I finish with that. Thank you.
Okay, thank you. And on to Aaron. And I'm just going to see if the panel can just slide slightly over so Aaron can come a little more into the group here. Yeah, thanks.
Thanks. Yeah, thanks so much to the organizers for the invitation. It was a little bit daunting coming to an economics conference. I didn't know what a discussant was until yesterday, and the concept kind of scares me a little bit. But I think overall it's been really good. So my name is Aaron Klasky. I'm a staff scientist at the University of Toronto. I work in the Acceleration Consortium, which is kind of a unit within U of T. It was born out of, speaking of science funding, $200 million from the Canadian federal government to basically establish this user facility, this hub of kind of center of excellence to build self-driving labs, as we've kind of explored before, for materials discovery. And so as a whole, we have about 30 staff scientists like me who work full-time in kind of building these labs for different applications across sort of inorganic chemistry, like battery technology and catalysis, onto sort of drug discovery as well, and polymers and thin films. And personally, I work on formulation science, which actually I think is a really good segue based on what people have spoken about here, because the combinatorial space, pretty much by definition, is massive, because that's our whole science. We're not synthesizing brand new compounds, but we're combining them in sort of strategic or insightful ways to get products at the end. We're very application-minded. Some of the things I work on, for example, are like personal care products and cosmetics, skincare formulations, and trying to like dig into not just how do we make them, but how do we understand how they come together, represent that kind of information, and try and accelerate that process, and kind of shift what we do from, not to shoot myself in the foot, but from kind of the art of formulation to try and make it a bit more of a data-driven process, essentially. And in doing that, we build, so we work, I know Keith personally, we work on similar kind of SDLs, trying to build sort of robots and AI in tandem that we then deploy for these different problems. And I agree, like I've thought a lot about, so I'm very new to this, I'm maybe 2 years into the Acceleration Consortium. I never touched AI or robots or anything like that before. And so I feel like I'm kind of living the transition myself and kind of the adoption rate and what it's good at and what it's not good at. And for better or worse, at least in my experience, a lot of the work that we've done so far in trying to build out our machine learning models and AI models, I think has kind of exposed a little bit the weaknesses of the sort of scientific infrastructure that we kind of rely on around things like reproducibility, reporting standards, data quality, all of that. If I go back to the list on the slide that Ajay mentioned, the kind of like the 3 things Google says you need to use and you need in order to have a successful project, and one of them is a lot of good data. And I feel like that's the bottleneck that we keep kind of running up on. And we circumvented it, we try and use our own intuition, we build smaller models, we try and be more specific about what it is that we tackle. And I think that works, but functionally, like we can't put like a big model on top of like 300 data points, right? And so that's one of the things that I feel like I flip-flop on a lot, and I believe in the power of kind of automation and democratizing this kind of automated research and self-driving labs. I think it's incredible, but I also think beyond incredible, I think it's absolutely like necessary. A lot of the work we do, so for example, in personal care and cosmetics, we work with natural materials, so things like shea butter, petroleum jelly, coconut oil, which if I got it here versus in Toronto versus in Japan versus in Brazil, they're all going to be different. How do we represent those ingredients to an AI so that it understands the difference? What chemicals are actually in there? They're mixtures of like 50, 60 different things. And can we even really learn from that? It's all kind of noise. And on top of that, that's just the ingredients itself, the actual processing. A lot of sort of making these materials, a lot of them are emulsions, they're self-assembling, they're irreversible, they're really sensitive to things like temperature and humidity and other stupid kind of like annoying logistical challenges that people are very not good at tracking and writing down and sort of like maintaining and thinking about. And that's where I really see the power of automation, but it's also why it's such a huge bottleneck, because if your robot can't do that either, you're kind of just, what are you even really building, right? So you're trying to focus on, we want to democratize this, we want to build big data sets that are like impactful and useful for us and for everyone, but in order to do that, it's a huge kind of learning curve. And I think it came up a little bit on like who needs to be in the room. I've talked about data like structure and standards so much more now than I did in my PhD, for example, because I had like 20 data points in my PhD, and now we're trying to share this across organizations and track things and be smart about it. And you realize like it's not just whether or not AI is good. You kind of need the whole architecture and the whole infrastructure around it before you can really turn it on and deploy it. And I think from the biomedical field and sort of drug discovery and AlphaFold, and they've done a very good job at trying to kind of push that standardization and that sort of being able to use these large data sets. But a lot of chemical sort of like chemistry applications, like formulations, for example, is just not there at all. And so we have big dreams about where we want to kind of build and what we want to achieve, but we keep kind of coming up on, well, we need the data to do it, and we need to build a system to build the data, and da-da-da, and then that's, to be honest, where I spend a lot of my time. So I'm interested to hear the different perspectives, because that's been my personal lived experience. But I really think the AI adoption is exciting, but it's very uneven across the different fields and across the different institutions. And I think parsing that out will be really interesting moving forward. Thank you.
Excellent. Okay, thank you. I'm going to ask 5 very fast lightning round questions, so just one sentence responses. You're going to be tempted to give examples and qualify your statements, but don't do that. Just one sentence response to each of these questions, and then we'll open it up for broad Q&A. Okay, so lightning round questions. For us, people who are not scientists of that, of your type, it doesn't seem to us that there's a whole bunch of increased productivity in science. In other words, we don't see all of a sudden a flood of new drugs or new materials or new designs of things at a much faster pace than what we did 10 years ago. So from our perspective, it seems like despite all the things you're describing, there must still be bottlenecks in the process. So I'm just going to ask you each, what do you view as the number one bottleneck to a substantive increase in productivity? So when we say productivity, we mean output per unit input. So for the same amount of capital and labor, let's say to doubling the amount of output, what do you view as, I'm sure there are many bottlenecks, but if you were to say this is the core bottleneck that is really preventing us from significantly accelerating what we do, what is the bottleneck? Just work our way down, one sentence each.
Synergistic sharing of data from multiple labs such that it is collected in a way that multiple groups can use it and that it has standards and is broadly usable. Those are all like apostrophes and commas.
Okay, data, obviously, high quality data, developing the tools, which takes time, and then teaching people how to use the tools and what the limitations are.
In one word, humans. Change management. Actually using it. And large companies to deploy this, I mean, I gave you just 3 testimonials.
Wait. Go ahead.
I would say physical validation, like actually realizing the predictions and things that we actually want to make.
Okay, second question. From a layperson's perspective, what will we observe first? That, in other words, when the final bottleneck falls and the speed up starts happening, what will it look like to us as we're just sort of out in the economy doing stuff when this self-driving machinery hits full flight? Well, Aaron, why don't we start with you?
Oh, no.
We'll get to the time frame in a moment, but in other words, we're working towards something. And what will it look like when these self-driving processes you've worked out the bottlenecks?
I still think, okay, sorry, I know it's one sentence. Short term, I think we'll still see like step change, like incremental improvements in things that we already kind of know, like better drugs, better plastics, better materials like that.
Okay.
Faster, better, cheaper materials, molecules, higher productivity, lower cost.
better medicines for patients and more precision medicines.
Shorter latency between acknowledging a problem and finding a solution.
Okay. Third question, which is from the scientist perspective, so no longer lay people but scientists, of all the different areas of machine intelligence and their uses in different parts of the process, where do you view as the most current enthusiasm? In other words, what's the area where there's the most enthusiasm that of AI applied to X in your domain, like whatever domain you're working in, whether it's hypothesis generation or in the testing phase or in the molecule discovery phase, or whatever it is that you're in the pipeline that you work on. Aaron, why don't we start with you?
Sure. For me, it's the agentic workflows, like connecting together disparate workflows into nonlinear and parallelized sort of procedures.
I would say two things. Working on more exciting, more difficult problems that they can tackle, and if you use the robots to not having to do the tedious, repetitive tasks that are just boring.
I think it is AI agents and the ability to generate them rapidly to connect different machine learning models together and see that effect. Cumulative effect.
I would say knowledge compression from many papers into small bits of information, and knowledge expansion from a bullet point to a paper, sadly.
Okay, two more, and then anyone who's keen to ask a question, please go to the mic. This one's just a yes or no question. Okay, will we see a fully closed loop in science by 2030, where the entire, so Herman, you did a little bit of duck and weave in your opening comments because you said, who's been in a Waymo? People put up their hands. And then you said, we're like Waymo. And then you said, we augment, we don't replace. But Waymo replaces. Okay, so there is no human driver in a Waymo. So the beauty of a fully closed loop is that the AI generates a hypothesis, comes up with a way of testing the hypothesis. The robots test the hypothesis with the test tubes and the pipetting and so on, observes the outcome from the test, updates its hypothesis, and goes again. And it can just go 24/7 and be generating data and knowledge as it goes. So can we get to closed loop by 2030? Just yes or no?
Yes, because it does exist. Oh, sorry.
Okay.
Yes, 2027.
No.
Yes, 2020.
Okay. So let me now give you each like 30 seconds to explain your answer. And you can go first.
I mean, so you didn't put writing a paper and publishing it in that loop. Even that's been demonstrated. But what you're describing of constructing a hypothesis and testing it, that has been proved by numbers of papers going back, I would say, actually the first one I can think of is 2006, maybe 2007. So yes.
Okay, but in other words, then once the result is generated, in other words, there's a physical testing, results generated, and then an automated updating of the hypothesis.
That's right.
and doing the loop. And what was the category that work is in? Like in
So
material science?
No, in biology. The very first example I know of in this is in yeast genetics, where it was a whole pipeline. This is the Ross King's work. I mean, others can disagree with me later, but this is an example of generating hypotheses, conducting experiments, and updating hypotheses in an automated fashion with no human involvement. And that's been, that's a 20-year-old demonstration. And people have moved into material science in recent years and done this in a lot of other fields. So, I mean, I think the sophistication of the kinds of hypotheses people ask and the ease of that part has gotten a lot better. Now we have, that can be turned into a paper that can then get disseminated more broadly. But, I mean, the core idea of can we close the loop? Yes.
Okay. Diane, you said no.
Well, so I would say yes to what you said. But I think I said no because I was thinking more about the drug discovery process. Like, there's no way that that's going to happen even probably in 10 years, right?
Okay. And the key bottleneck to that happening?
I mean, there are many bottlenecks, right? It's the data, but it's also just the coordination between different groups that do these different tasks now. and how to make that so flow.
Okay.
right?
And
Yeah,
Herman,
to-
you
to
said
qualify,
yes at
yes.
27, so
In
you
fact-
shortened the timeline.
I mean, in fact, I agree with Keith. I mean, this has been done, but depends what level of 24/7 self-driving lab.
Okay.
And to clarify, when I say augment, I don't think if the scientist was driving the car before, we don't replace them. They sit now in the back of the Waymo, and they have time to read a paper, to write a paper, to think, to use their imagination and creativity, sitting in the back and still in control, human in the loop. You can still tell that Waymo, not only I want to go from point A to point B, I may want to stop on the way and pick up something. And so the scientist is sitting now in the back, in the loop and in command, in our view.
Okay.
Yeah, I said yes. And yeah, to Keith's point, like it does kind of already exist. Closing the loop is a super common term that we use, at least internally, and I think across the SDL world. I think the main difference, and maybe I'm reading into your question, is the scope of it. We have a closed loop platform that mixes surfactants and measures contact angle, and it can decide how to like adjust them to get the best contact angle. That already exists, and that's great, but that's not solving big problems. It's not connecting complex workflows and all of that. But I will say, like, our acceleration consortium funding runs out in 2030, so I would hope that we expand the scope and the ability of our closing the loop moving forward. But I do think we're on the path there. Yeah.
All right.
Do you
Any
agree that
questions?
So I had to add
the
one
technology
quick-
is ready, no?
Yeah.
We agree on that,
Yeah.
no?
I mean, like I talked about different stages of drug discovery process. I think you could close the loop probably in each one of them, but it's like connecting them. That's hard.
Okay, Joel.
So this has been terrific. It's all fascinating. You keep, many of you, using the word data. And so what do you mean by data? Is it proprietary, private data? Is it the sort of thing that can be leveraged across environments, so the government should be involved? What do you mean by data, and who's going to be suing whom?
Can I
Yeah,
start?
go ahead.
If I may start on our end, high quality, reproducible data that is machine learning ready. It can be proprietary or, I mean, if you think about it, there's actually, it was either Nature or Science published a survey of 1,500 scientists agreeing that there's a reproducibility crisis. The published data is not, in the majority of cases, not reproducible. So that's what I mean. It can be proprietary or ideally public.
And you mean experimental data?
Yeah, the ground truth, actual, data, lab validated data.
So we all here do research, but we also teach, and we have students who worry about what jobs are available for them when they leave the classroom. And I'm kind of curious if you could talk a little bit about what role there is for entry-level workers in this type of science, right? So you talked about time being saved, but whose time is it being saved, right? So the scientist sitting in the backseat of the Waymo wasn't doing all of the grunt work before, right? He was managing a lab, and there were students doing that. And so what role do the entry workers play in this type of system?
Yes.
Anybody else want to?
Well, as a person that develops self-driving labs, there's lots of work to be done. So, I mean, the students in my group that, develop new pathways for automation, I mean, there's a lot of basic questions to be asked. I mean, things like, thinking about some of the complicated materials that need to be evaluated, the way that we've done research in the past is very human intensive, and figuring out the right way to measure equivalent properties and get the right information with an automatable system is a really deep kind of itself a field of science. So there's like lots of questions to be asked there. And even if we were to discover the perfect robot today, we'd still need to have, a whole field of study around how to figure out the sort of automation ready proxy measurements that let us do this materials development. It's not going to just be, we suddenly have the database of all possible materials using the measurement that we're used to. So there's a lot of basic science and a lot of entry level, teaching and research that needs to be done around sort of developing that infrastructure. And that's not going to change.
Please go ahead.
Thank you for sharing. My question is how you balance progress with safety and cooperate with other major players globally like China.
Would you like to take that one?
Sounds like a Canada question. You guys have done a lot in safety. The Acceleration Consortium is that the Acceleration Consortium has, from the very beginning, prioritized safety. So that was what I meant by that.
Yeah. I think this, especially in like academic labs, it often it ends up being kind of like there's a lot less oversight over the safety, and people are like, we're introducing these robots that fling around everywhere. who's going to get hurt, right? And what controls are there? So there's been a lot of work in sort of certification, like electrical certification, safety, sort of like physical movement, and trying to like trying to build our labs such that humans can operate within them. They're not kind of robot only. I think has been really helpful. But to be honest, it's still kind of nascent because we don't know what kind of there's new agents that come out that can predict if I make this molecule, it will be toxic, so I'm going to choose not to. I think that stuff is interesting, but it's still a little bit new in development. But it's going to become a much bigger question, I think. Yeah.
And I think a lot of times, like, the data is not reproducible that's published because it's a different standard that's being applied in academics versus in industry. And the pharmaceutical industry, certainly, because you're dealing with human patients. I mean, there are so many, it has to be super robust. And so we really want data at that level.
I'm not sure if the safety he was referring to was safety of scientists getting knocked over by robots or weaponizing viruses and things like that, and to the extent to which this makes sort of, science much more accessible and, can be used for both good and evil. We can come back to it if somebody wants to. Please go ahead.
But absolutely seconding that question too. I have two you can pick from. You mentioned that you're developing AI alongside the automation of the lab. Can you explain a little bit what you're doing there and whether a frontier model could just run everything, or why not? Why you need to have specialized LLMs or AI? And
let's stop that. That's a good one. Yeah, let's go ahead. So in other words, all the specialized stuff, and like many other domains, these frontier models are just rolling into lots of different applications. Do you think that they can just do this?
I mean, people have studied that question. I would say that finding ways to, and Eric talked on this a little bit about trying to say what material I have and how do I adequately explain what that material is to even a frontier model. That's a research question, and people are studying that. And people have explicitly studied this question of, so I have kind of forefront statistical methods to choose experiments, so advanced DOE, and I can compare that to just giving the data to an LLM and asking me what to do next. And depending on the context, if there's if that's a field with a lot of context, the frontier model can do very well. But if it's not, then it won't. So it really just depends on the problem and the context you can give it. So, I think people are definitely exploring this. It's a future that I think is really exciting because we can use these to do a lot better. And LLMs have done a lot for integration of hardware and coding, as was talked about earlier. So there's, they've already played a big role in this, and so they will continue to be a big part of the software part of this chain.
And then once this takeoff has happened and they're flying on autopilot, how do you envision knowledge aggregation and transmission into society, and then maybe also aggregation at the worldwide level?
I'm going to pause that because I want to stay on the science part for now. Let's go to the next question.
This is sort of a follow-up to David's question about the people. I guess I'm still struggling to discern whether to what extent in the world that you're building and envisioning, humans are augmented by AI and in turn augment AI, or are replaced by it, and are there any general principles that you can identify at this point that would help us to sort of sort those tasks into different buckets that are going to be affected differently?
I mean, I don't think that it's going to replace humans. I think that it may replace certain jobs that humans currently do, right? And that the workforce will need to adapt to those changes.
Creative destruction, right? So yes, some jobs are going to change or disappear, but others will be, expanded. To some of the previous question, how many materials are out there that we can discover? Just small molecules, 10 to the 60 potential new molecules. So the goal is to deploy this broadly and be able to solve and tackle other problems that are today not being tackled. So that should expand, grow the pie.
I mean, I think that's part of it too, where if you can code more quickly and develop the models, then you can ask 100 times more questions than you could ask before, where you could only ask one question, right? So you're generating more knowledge.
Okay, since we're almost out of time, I'll let each of the people behind the mic say your question, and then I'll give 30 seconds to each of the panelists to say whatever they want to say in response to any of those questions.
Okay, this is a bit more directed towards the material scientists. So Diane kind of walked us through, like, how LLMs might be used at lead generation all the way to like clinical trials. So I'd love to hear the material scientists sort of touch a little bit on, like, getting from stuff you do in your lab to sort of like things in factories. Like, what are the what is the role of AI automation there? What's the sort of the equivalent of the clinical trial look like for you guys?
Yeah, it was really nice to see how, on the one hand, you had similar answers to the questions of, but also that there was enough heterogeneity in your answers, so differences in terms of how you use AI and what the impact is. That's what we need as economic researchers here. We need to work on that heterogeneity to try to explain why. So very good to hear. But my question goes to Aaron. You have an example of where an institution like the university is actually also involving in the uptake of, so what kind of bottlenecks are you trying to address, market failures that actually the individual labs would not be able to? And then secondly, why would it then be important to have public funding for that? So what is the extra reason why you would need public funding for having that university level?
My question is for AJ regards the closed loop. So we have this thing that is in science, is peer review. So the peer review, is it a bottleneck? Or where do you place it in the stages? Could it be maybe the thing that we are not, so the closed loop is not acting and we're not in this closed loop because of peer review?
Just thank you all for an amazing, I've got a page full of questions that I know Ajay is not going to let me ask. So, but the one that I am going to ask is, like, science and discovery are famous for sort of mistakes and serendipity and things that are kind of totally go wrong, but then, oh, we now have penicillin. So, like, how do I think about AI with that type of discovery?
Okay, 30 seconds each. Go ahead.
A lot to respond to. Thanks for the great questions. Knowledge is for people, right? So we're generating knowledge, we're doing peer review, we're generating papers so that we can understand the world better and apply things better and ultimately increase the quality of human life. And so that's got to be core to it. And it's all right if there's some latency in that. I think that doesn't mean we can't, generate a lot more data and make much better answers to questions. So that's a bit in response to a couple of questions. Lab to factory, I do want to touch on that in the last 5 seconds, is that some of the same processes we're talking about for discovery are being applied in development. So all of the things we're talking about are being applied across the board. So I expect we're going to see the similar processes. As we accelerate the discovery materials, we'll accelerate their application in different products as well. I've exceeded my time.
So I think peer review is super important, and both in terms of papers, but also just in terms of like feedback on the models. I think that we're a long way from that not being needed. I also think we do need government agencies to step in and help us to collect the right data in a uniform way. Otherwise, it's being done in different ways in different places, or it can be done in different places, but there has to be a standard that's set up, which is what the Protein Data Bank did. Set these standards, and people deposited these structures over like 30 years, and actually more than that. But and that's what enabled AlphaFold. So I think we really do need that piece.
Yeah, so 30 seconds. AlphaFold is a great example of collaboration and having reliable data. So what enabled AlphaFold is the database of protein structure that was good quality, that was trained on. Without that underlying data, like the ground truth or the reproducible lab-validated data, you cannot train those foundation models and all those. So that's fundamental. There's many bottlenecks along the way. Again, human is a lot of that. In drug discovery, clinical trials have so many different bottlenecks, and that can be improved. So there's many steps that it's going to take a while until we see, this continuum of new drugs being developed that come to market. That is going to take some time. And finally, on the serendipity and penicillin, with robots and this automated, seamless process, you can have many more shots on target that humans will have to try to understand, okay, why are we seeing this interacting with the agents and technology?
Yeah, thanks so much for the questions. Maybe I'll address kind of the public funding question. So the Acceleration Consortium exists as part of U of T, and our first goal is obviously to build cool things and do cool science and talk about it and sort of build that ecosystem. But part of it is also the training and the democratization of all of it. That I think that's like a very, at the forefront of our kind of mission is building open source tools, sharing them widely, training graduate students and undergraduate students who are probably rightfully concerned about their own careers, and upskilling and bringing professors in who can say, I can't buy this $1 million platform, but I can work with you, build a cheaper one, and still sort of contribute to this overall field. And to me, I think that's a really kind of honorable thing. On top of the sort of data sharing and like actually like building public goods from data, I think we can also do it from hardware, and you know, we can learn from our mistakes as well. It probably won't work for everything. That's kind of where we see ourselves and why I think this public funding is so important. Yeah.
Excellent. All right, well, to our panel, I'll say, look, economists aren't that bad. Thank you very much. You stepped out of your comfort zone, and you took the lightning questions with good humor. I really appreciate that, and you also taught us a lot. Thank you very much.
And I just want to say thank you to Ajay for doing such a masterful job of running the panel. And thank you to all of you for being here to the very end. We have lunch in the Monteverdi room. All right, so thank you again, and hope to see you all next year.
Thanks,